A finger presses one key. Somewhere inside the machine, a physical change begins. Later, one exact mark changes on the screen. Keep that whole journey in view. We are going to open only its first link, ask what is physically different there, and close it again before moving on. If this first link is vague, every later explanation inherits the vagueness. Begin with an ordinary wall switch. It has two dependable resting positions. A tiny wobble near the lower position does not make us mistake it for the upper position. The same is true near the upper position, but halfway between them, while the switch is moving, we should not pretend that it is safely in either resting position. The useful relation is two stable regions separated by an uncertain journey. A computer component is not a hand-operated lever. We are borrowing only that relation. Now keep the relation and replace the lever with something measurable at a circuit input. One such quantity is voltage, an electrical difference measured between 2 points. As conditions change, the measured voltage may take many values. That changing measurable condition is a physical signal. Electricity is not a little switch handle traveling through the wire. The comparison has carried us to the idea of dependable regions. It must stop there. A designer can specify a lower valid region and a higher valid region. Small variations inside either region are tolerated. Between them lies a transition or invalid region, where the receiver is not promised a safe answer. The exact thresholds depend on the device, its power supply, temperature, and other physical details, so this picture deliberately gives no universal voltage numbers. The rule is about bounded regions, not about one magical dividing value. Try the rule before seeing the labels. Measurement A sits well inside the lower valid region. Measurement B sits in the middle. Measurement C sits well inside the higher valid region. Which measurements may the receiver classify safely? A is safely lower, C is safely higher, B is neither promised result. Choosing whichever side looks closer would invent certainty that the physical contract does not provide. Now add an agreement. When the measurement is in the lower valid region, the receiver records 0. When it is in the higher valid region, the receiver records 1. 0 does not universally mean no electricity. A lower valid measurement can still be a real non-zero electrical quantity. 0 and 1 are names assigned by the receiving rule. Another technology may use different physical conditions while preserving the same two-way agreement. Change the carrier. Instead of a circuit measurement, imagine a place on a card that is either covered or punched open. The material, shape, and sensing method have changed. Yet one relation survives. The receiver must distinguish one allowed alternative from the other. The useful thing is not voltage, paper, darkness, or light by itself. It is a dependable choice between two declared possibilities. That dependable two-way choice is 1 bit. A bit is an abstract value with two possibilities, commonly written 0 and 1, represented by some physical condition. The physical details matter because they determine whether the representation is reliable, but the bit is not made of copper, voltage, paper, or light. Those are carriers. The bit is the classified choice the system preserves. So when people say that a bit travels along a wire, do not picture a tiny bead with a 0 painted on it. A physical disturbance changes along the path. At a receiving boundary, circuitry classifies the local condition according to its valid regions. Later stages may produce fresh physical conditions representing the same value. What persists through the explanation is the declared 0 or 1 relation, not one microscopic object making the entire trip. Return to the whole machine. The key press creates a physical change. A receiver accepts measurements in declared valid regions and rejects the uncertain middle as unsafe. An agreement names the two reliable outcomes 0 and 1. That classified two-way choice is a bit. We have not yet explained how choices are kept, calculated with, or turned into a mark on the screen. We have earned only the first link. The next question is now precise. How can several such choices remain in order while the machine moves them and uses them? Keep the first link of our machine in view. A physical receiver accepts one of two dependable regions and records 0 or 1. But those names are not hiding inside the voltage. If the physical carrier changes completely, what can remain the same? We will keep one two-way choice fixed while its form changes around it. Imagine 8 small shutters. Each may be closed or open. We agree that closed stands for 0 and open stands for 1. The shutter is the carrier, its position is the physical state, and 0 or 1 is the assigned value. This models only the relation. A computer does not contain these shutters, and opening one does not send a tiny numeral through the machine. Replace the first shutter with a patch that is dark or bright. Let dark represent 0 and bright represent 1. The material and sensing method have changed. The declared alternatives have not. A magnetic region pointing one way or the other can preserve the same choice again. The comparison carries only distinguishability and agreement. Light, magnetism, and voltage do not behave physically alike. Now the labels disappear. A low valid voltage, an open shutter, a bright patch, and one magnetic direction appear with separate receiving rules. Predict each value. The answer is not whichever state looks more like a 1. It comes from applying the declared rule. Under a different rule, the same physical state could be assigned the other value. Keep 3 ideas separate. The carrier is the physical thing or measurable condition. The encoding rule assigns values to allowed states. The value is the abstract 0 or 1 that later logic uses. These are connected, not synonymous. Calling a wire a bit is loose speech. More precisely, the wire carries a condition from which a receiver recovers a bit value. Build the row one position at a time. Each new cell contributes one independent two-way choice. Position matters: closed, open. Closed differs from open, closed, closed, although both contain the same states. A notch gives the row an orientation, so positions cannot silently reverse. Nothing is yet a number or letter. We have earned only an ordered pattern of bit values. One position has 2 patterns. A second independent position pairs each first choice with 2 more, making 4. A third doubles the total to 8. Continue through 8 positions. 2 multiplied by itself 8 times gives 256 patterns. This count gives them no meaning. It tells us how many ordered alternatives 8 bits can preserve. 8 bits are commonly called a byte. The shutters flatten into the notched 8-cell carrier that will travel through our machine. Byte tells us there are 8 ordered positions. It does not tell us whether the pattern is a number, text, an instruction, or anything else. The word fixes width, not purpose. Test a new carrier. 8 punch positions pass a sensor. Material present means 0. A hole means 1. Read from the notch. The pattern is 0, 0, 1, 1, 0, 0, 1, 1. Photograph the states as dark and bright cells under a matching rule, and the ordered values remain. If one position is torn and unreadable, the abstraction may not invent a bit there. Close this part carefully. A bit is one abstract two-way value represented by a physical carrier under an encoding rule. 8 ordered bits form a byte with 256 patterns. The notched carrier has a stable identity, but no meaning painted onto it. That leaves our next exact question: when the pattern stays unchanged, where does meaning come from? The notched carrier returns with 0, 0, 1, 1, 0, 0, 1, 1. None of its cells will change. 3 receiving rules approach instead. One says 51, another says the character 3, and a third divides the bits into fields. Has one made a mistake? The answer depends on a distinction we have not yet made. Consider the mark 10 on a door, a bus, and a football shirt. The same shape can be a room, route, or player number under different conventions. The mark maps to our unchanged pattern. The convention maps to the receiving rule. The limit is important. Computer rules must be exact enough for circuitry, not guessed from social context. First, apply an unsigned whole number rule. The rightmost position is worth 1, and each position leftward is worth twice the previous one. 2, 4, 8, 16, 32, 64, and 128. Ones here activate 32, 16, 2, and 1. Their sum is 51. The pattern did not change physically. A declared place value rule produced that reading. Remove the number scale without touching the carrier. A text decoding rule uses the pattern as an index. In ASCII, index 51 names the written digit 3. The byte is not a tiny picture of that digit. A later font system will choose its pixels. Number 51 and character 3 are therefore different interpretations of unchanged bits. A third receiver treats groups of positions as fields. One field might select an operation, another a register, and another a mode. The visible separators do not cut the byte or change any bit. They show which questions a decoder asks of which positions. Not every pattern must be a legal instruction. Legality belongs to the exact instruction contract built later. Meaning is not a substance added to the carrier. It results from a defined receiving operation. A whole number rule adds activated place values. A text rule selects a code table entry. An instruction rule uses fields to select control alternatives. The bits supply distinctions. The receiver supplies their use. A byte can therefore be copied perfectly, yet produce the wrong result in the wrong context. Try 0, 1, 0, 0, 0, 0, 0, 1. The unsigned rule gives 64 plus 1, or 65. ASCII entry 65 names capital A, which fact stayed constant, the 8 cells, which changed. The receiving rule. If another system defines no meaning for this pattern, undefined is correct. Resemblance is not permission to guess. Interpretation is separate from location, movement, and storage. A pattern may rest in memory, appear on a rote, or be captured in a register. Those facts answer where represented values are and whether they persist, not what they mean. The same notched carrier will remain visible, so a route never masquerades as meaning, and a container never masquerades as its contents. Send the byte for character 3 to an unsigned adder. The adder does not see a written 3, it sees numerical 51. Adding 1 gives 52, whose ASCII reading happens to be character 4. That useful coincidence depends on the table's design. The machine did not understand counting characters. Exact rules composed, and a different encoding could produce something else. Avoid 2 mistakes. Bits need no human observer before physical receivers can apply encoded rules, but a pattern also carries no single eternal meaning within itself. Wiring, timing, conventions, and the current operation give it a role, meaning in our machine will always be tied to a specific receiver and an inspectable rule. The interpreters withdraw, leaving the octet unchanged. Different declared receiving rules can give one pattern different valid interpretations. The carrier represents ordered values. A context-specific operation determines their role. Our machine can carry distinctions but cannot yet make a logical decision. To earn that ability, we need one exact input-output promise in every case it covers. Place 2 bit values at an unknown module. It must produce a third bit by a dependable rule. The physical circuit underneath involves transistors, voltages, energy, and delay. Here we describe the Boolean relation. Each input and output is 0 or 1. This boundary does not erase physics. It lets us prove the relation independently of one physical implementation. The module is a NAND gate. Its promise can be spoken in one sentence. The output is 0 only when both inputs are 1. In every other allowed case, the output is 1. The name joins 2 ideas and asks whether both inputs are 1. The N at the front means the answer is inverted. But the name is only a memory aid. The full promise lives in the 4 cases we are about to test. 2 inputs with 2 values make 4 possible pairs. 0, 0 produces 1, 0, 1 produces 1, 1, 0 produces 1, 1, 1 produces 0. No 5th Boolean case is hidden, because the table contains every allowed pair. Checking all 4 verifies the abstract promise. 3 rows would not be enough. The missing row might contradict the rule. Predict the output before the final row is revealed. The left input is 1, and the right input changes from 0 to 1. At first, both are not 1, so the output is 1. After the change, both are 1, so the output becomes 0. Now reverse only the left input. The output must return to 1. If a proposed NAND module remains at 0, that single counterexample is enough to reject it, however correct its other rows may be. A guarded doorway offers an analogy. A warning lamp stays on unless both inspectors present approval cards. Each card maps to input 1. The lamp maps to the NAND output. Missing either card keeps it on, and showing both turns it off. The analogy stops there. A real gate does not inspect or approve. Its output follows physical behavior within electrical and timing conditions. The table assumes every input is an accepted 0 or 1. An invalid voltage is outside its promise. Physical output also changes over finite propagation time. Different technologies can use different structures and thresholds while implementing the same table. The table tells us the required relation, not every fact about how matter produces it. Now feed the same input into both NAND entrances. When that shared input is 0, the pair is 0 and 0, so the output is 1. When the input is 1, the pair is 1 and 1, so the output is 0. The output is always the opposite of the input. One NAND has therefore made not. This is our first constructive step. We did not merely claim that NAND can imitate another rule, we traced every possible input to prove it. A NAND output is the opposite of AND. Pass that output through the NOT construction and it becomes and again. Not each input first, and then NAND those results and the output becomes OR. It is 1 whenever at least one original input is 1. The next chapter will expose every wire and row of these constructions. For the present claim, we have a route from NAND, alone to NOT, and OR. Why are those relations enough? For every truth table row whose desired output is 1, and conditions matching that row using NOT where it requires 0. Each term recognizes one row. Or those terms together and the result is 1 on exactly the chosen rows. If no row is chosen, A and not A supplies constant 0. Since NAND constructs NOT and OR, it can construct any finite Boolean truth table relation. Functionally complete does not mean one NAND performs every task or is always the fastest, smallest, or most energy-efficient choice. It means NAND-only networks can express every finite Boolean input-output relation. Storage still needs feedback and timing. Arithmetic needs many composed relations, and a computer needs far more than gates. Completeness gives sufficient logical material, not a finished machine. The tested rows close into a certified NAND outline. Whenever it returns, only 1, 1 produces 0. We may reuse the module without replaying its internals, but may never change its contract. Next, we will arrange copies of this proven decision into new decisions and verify that composition does not conceal an error. One certified NAND module stands at the center. We will never ask it to do anything beyond its 4-row promise. Instead, we will connect outputs to inputs and let several correct local relations compose into a new relation. This is how complexity will grow throughout the machine, not by renaming a mysterious box, but by building a network, retaining its intermediate values, testing every input case, and only then closing the network into a reusable module. Begin with NOT. One input route forks into both entrances of a NAND. If the input is 0, NAND sees 0, 0 and outputs 1. If the input is 1, NAND sees 1, 1 and outputs 0. There are only 2 possible input rows and both are now visible. The new outline may be labeled not because its output is always the opposite Boolean value. The fork copied a value to 2 inputs. It did not divide or weaken the abstract bit. For AND, the first NAND receives A and B. Its intermediate output is 0 only when both inputs are 1. That is the opposite of the result we want. Feed the intermediate value into both sides of a second NAND. Our proven NOT arrangement. The second stage reverses it. Now 0, 0, 0, 1 and 1, 0 all produce 0, while 1, 1 produces 1. The intermediate route remains on screen, so the final label cannot hide how the answer was made. Or should output 1 when A is 1, or B is 1, or both are 1. First invert A and invert B with 2 NOT constructions, then NAND those inverted values. When both original inputs are 0, both inverted inputs are 1, so the final NAND outputs 0. In every other original row, at least one inverted input is 0, so the final NAND outputs 1. This is De Morgan's relation made visible as moving values, not quoted as a spell. Hold the input pair A equals 0 and B equals 1. Predict each route. Inverting A produces 1. Inverting B produces 0. NAND of 1 and 0 produces 1. So or is 1. Now change B to 0. Both inverted roots become 1, and the final output becomes 0. The answer changes because the declared intermediate value changes, not because the final gate somehow knows the word OR. Now build a sharper relation. X, or, called exclusive OR, is 1 when inputs differ and 0 when they match. The rows are 0, 0 gives 0, 0, 1 gives 1, 1, 0 gives 1, and 1, 1 gives 0. Ordinary, or cannot do this because it outputs 1 for 1, 1. We need intermediate states that distinguish exactly one high input from 2. Construct 4 NAND stages. First, N1 is NAND of A and B. Next, N2 is NAND of A and N1. In parallel, N3 is NAND of B and N1. The final output is NAND of N2 and N3. These names are temporary ledger entries, not new mysteries. We will keep all 4 values exposed while each input row travels through the network. Trace the matching row 0, 0. N1 becomes 1. N2 sees 0 and 1, so it becomes 1. N3 also becomes 1. The final NAND sees 1, 1 and produces 0. For matching row 1, 1, N1 becomes 0. Then both N2 and N3 see 1 and 0, so both become 1. Again, the final NAND receives 1, 1 and produces 0. Matching inputs have reached the required 0 by 2 different internal traces. Now trace 0, 1. N1 is 1. N2 receives 0 and 1, producing 1. N3 receives 1 and 1, producing 0. The final NAND sees 1 and 0, so it produces 1. Swapping the original inputs swaps N2 and N3, but leaves the final answer 1. We have now tested all 4 rows, 0 for matching inputs and 1 for different inputs. The 4 NAND network has earned the X or contract. This resembles composing simple moves in a recipe. Each step has a known input, an operation, and an output that becomes the next step's input. The mapping is the chain of dependable local transformations. The limit is that logic signals are not ingredients consumed or mixed into a substance. A gate establishes a new physical output representing a value, and several downstream inputs may observe that value subject to the electrical limits of the implementation. In the abstract table, intermediate values appear in logical order. In a physical network, each gate has propagation delay. 2 roots with different numbers of stages may settle at different times, so an output can briefly pass through a value that is not the final stable answer. Later, timing rules will tell storage when it may safely capture a result. Our diagrams therefore distinguish a root that is changing from a value that has settled. Instant, perfectly simultaneous motion would make the picture easier and the explanation false. One last network arrives without a label. Its first stage makes NAND of A and B, and its second stage inverts that result. Predict the output for all 4 rows. Only one survives as 1, the other rows become 0. That is, AND. The test matters because it asks you to recover a contract from operations rather than recognize a familiar outline. If the internal roots are traceable, a new arrangement is a problem we can solve, not a symbol we must memorize. The working drawings close one by one into certified NOT, AND, OR, and XOR modules. Their outlines are now compressed proofs, not unexplained decorations. A future scene may reopen any one of them to the exact NAND routes we have traced. With these relations, the machine can combine and compare values. But another need is about to appear. Sometimes 2 candidate values are both available, and one control value must choose which candidate is allowed to continue. 2 settled bit values wait on separate routes, A above and B below. The next part of the machine has only 1 input. We do not want to combine the candidates, and we do not want either one to be changed. We need a 3rd bit, called select, to decide which candidate is connected to the output relation. When select is 0, output A. When select is 1, output B. That exact need comes before the symbol that will solve it. Railway points give us a useful shape for the idea. 2 tracks approach one onward route, and the points choose which approach is connected. Candidate A and candidate B correspond to the 2 approaches. Select corresponds to the setting of the points. The output corresponds to the onward route. The limit is that our selector need not move a physical rail or carry a train. It is a Boolean network whose output value follows one chosen input after the network settles. Build the select 0 path first, invert select then, and that result with A. If select is 0, its inverse is 1, so this path passes A through. 1, and A equals A. If select is 1, its inverse is 0, so this path is forced to 0 whatever A contains. The route is not deciding whether A is good or bad. It is making A consequential only under one declared control condition. Build the other path by ANDing select directly with B. When select is 1, this path passes B. When select is 0, it is forced to 0. Finally, OR the 2 path results. The complete relation is not select and A or select and B. For either allowed select value, exactly one data path can affect the output. The other contributes 0 to the OR, and therefore cannot alter the selected result. Set A to 1 and B to 0. Before select moves, predict both possible outcomes. At select 0, the A path is enabled and the output is 1. At select 1, the B path is enabled and the output is 0. Now exchange the candidate values while leaving select at 1. The output becomes 1 because it follows B. The selector's promise concerns which position is followed, not which numerical value is preferred. There are 8 complete input rows because A, B, and select each have 2 possibilities, 2 times 2 times 2. We do not need to memorize 8 unrelated answers. In all 4 rows where select is 0, compare output only with A. They match. In all 4 rows where select is 1, compare output only with B. They match. Grouping the table by the control value exposes the same rule the moving roots just demonstrated. A selector does not remember either candidate. If A or B changes while that input is selected, the output follows after propagation delay. If select changes, the output follows the newly selected input after the roots settle. Remove the candidates, and nothing inside this Boolean contract preserves their old values. This is combinational logic. The settled output depends on current inputs. Memory will require a relation in which prior state can continue to matter. Do not confuse a selector with a decoder. A selector chooses one of several data candidates and produces one data output. A decoder receives a coded selection value and activates one of several choice lines. Railway language can make both look like routes, but their contracts point in opposite directions. Many data inputs toward one output for the selector, one coded input toward many mutually identified outputs for the decoder. We will build the decoder when memory needs one address to choose one location. Replicate the proved 1-bit selector 8 times. Align the copies with the notched carrier and share the same select value across them. Each copy chooses the corresponding position from byte A or byte B. No position crosses into a neighbor, and the notch preserves left to right order. The result is an 8-bit selector. Scaling has repeated a proven relation in parallel. It has not introduced a new rule or treated a byte as one indivisible physical lump. The selector closes into a certified outline only after both control cases have passed. We can now choose between current alternatives, 1 bit or 1 byte at a time. Yet as soon as the source changes, the old selected value disappears from this network. Our machine still has no state. The next construction must do something qualitatively new, preserve one allowed result after the brief input that established it has gone away. Every module built so far settles to an output determined by its current inputs. Change the inputs, and after delay, the old result is gone. But a computer must preserve choices: a partial calculation, the location of the next instruction, the character waiting to be displayed. We will begin with only one remembered bit. The challenge is exact. Establish 0 or 1 with a brief input. Remove that input, and still have the circuit's present state depend on what happened before. A spring latch on a door gives us the everyday relation. A brief push moves the bolt into one stable position. After the hand leaves, the bolt remains there. Push the release and it settles into the other position. The hand corresponds to a temporary control input, and the bolt position corresponds to retained state. The limit is crucial. Our circuit has no mechanical bolt. Its persistence will come from powered electrical feedback, and removing power removes that physical state. Place 2 NAND gates facing one another. The upper output, marked Q, feeds one input of the lower gate. The lower output, marked not Q, feeds one input of the upper gate. Each gate also has one external control input. The crossed routes mean each output helps determine the other gate's next output. This is feedback. Part of the circuit's result returns as part of its own continuing condition. We will not hide the loop inside a memory symbol until every allowed case has been traced. These external controls are active-low, shown by bars over their labels. 0 performs the named action and 1 leaves it inactive. This is an electrical convention, not a new kind of bit. A 0 on the set input requests set, a 0 on the reset input requests reset. When both are 1, neither action is requested. Saying this first prevents the common error that one must always mean do something. Begin in a known reset state. Q is 0 and not Q is 1. Drive the set input to 0 while reset remains 1. A NAND with a 0 input must output 1, so Q becomes 1. That one reaches the lower NAND. With reset still 1, its output becomes 0. The pair settles into Q1 and not Q0. Record before and after rather than letting motion erase the old evidence. Return the set input to 1, so both controls are inactive. Predict Q. The upper NAND receives 1 from set and 0 from not Q, so it remains 1. The lower NAND receives 1 from reset and 1 from Q, so it remains 0. Feedback sustains the pair after the request disappears. Current external inputs no longer determine output alone. Previous stable state also matters. That dependence on history is memory. Request reset by making the reset input 0, while set remains 1. The lower NAND is forced to 1. That returns to the upper NAND, whose 2 inputs are now 1, so Q becomes 0. Release reset to 1. The pair continues to support Q0 and not Q1. Set, hold, reset, and hold are now visible. One circuit supports 2 stable states, and a temporary control chooses which persists. One pair is forbidden. Set and reset both 0. Each NAND then has a 0 input, forcing both outputs to 1. The outputs Q and not Q no longer oppose each other, and both actions were requested at once. If both controls return to 1 nearly together, tiny timing differences can decide which stable state wins. The model promises no chosen result. Marking this invalid is part of the contract, not an inconvenience to conceal. Use the ledger on a fresh sequence. Initial Q is 0. First controls request set, then both controls hold, then controls request reset, then hold again. Before the animation advances, write the predicted Q column. 1, 1, 0, 0. The two hold rows cannot be answered from current controls alone because both rows have the same external pair. Their different answers come from the different states entering those rows. That is a direct test of sequential rather than combinational behavior. The stored bit is not detached from physics. While powered, the feedback network continually maintains physical output conditions representing its state. Noise margins, delay, loading, and power limits still apply. Remove power from this ordinary volatile latch and the maintained conditions disappear. Powering it again does not entitle us to claim its former value. Persistent storage will use different physical mechanisms and contracts. Here we have proved retention across changing control inputs, not retention across loss of power. The cross-coupled gates close into a 1-bit storage outline, but the before and after ledger remains beside it as proof of history. We can set, reset, and hold a state. What we do not yet have is an orderly moment when many storage cells agree to accept new values together. If control changes arrive at arbitrary times, a larger machine becomes difficult to reason about. The next chapter introduces a shared event that separates old state from new state without pretending that physical change is instantaneous. One storage cell can hold a bit, but a machine will contain many cells whose outputs feed logic and whose next values depend on one another. We need a clean way to describe when a proposed next value becomes stored state. The clock will provide a repeated reference event. It does not carry the data and it does not calculate the answer. Its active edge tells participating storage elements when to capture inputs that must already be ready. A camera shutter gives a limited analogy. The scene may move continuously, but the photograph records what the camera receives during a defined exposure. Here, the data input corresponds to the scene, the active clock edge corresponds to the capture event, and stored output corresponds to the recorded result. The analogy stops before optics and exposure duration. A digital storage element follows an electrical timing contract. It does not make a picture, and its edge is not infinitely thin in the physical world. Use an edge-triggered storage model with input D and stored output Q. Between active edges, changing D does not change Q. At each active edge, the element captures the accepted value at D. After a finite clock to output delay, Q represents that captured value and holds it until a later active edge. In speech, we may say Q changes at the edge, but the timeline will retain the small propagation interval so that the visual claim stays physically honest. Start with Q equal to 0. Well before the first rising edge, D settles at 1. The old state column remains Q0 right up to the edge. The edge arrives, the ledger copies D equals 1 into the new state column. After propagation delay, Q becomes 1. Nothing traveled from a clock lane into the data cell. The clock event authorized capture, while the data input supplied the value that was captured. After the first edge, change D back to 0 halfway through the cycle. Predict Q. It remains 1 because no active edge has occurred. The new input value may travel through the combinational route leading to D, but it has not yet become stored state. At the second rising edge, 0 is captured. After delay, Q becomes 0. The held output separates a proposal for the future from the state the machine currently owns. For capture to be guaranteed, D must be stable for a specified interval before the active edge. That interval is setup time. Think of it as a forbidden last-moment arrival zone on the timeline, not as a command to slow the data artificially. If D changes inside that zone, the storage element's contract does not promise which value will be captured. The correct diagram marks uncertainty. It does not choose the nearest side for the sake of a neat animation. D must also remain stable for a specified interval after the edge, that is hold time. A change too close on either side can disturb the physical capture process and may leave the device temporarily unable to present a valid 0 or 1. This is called metastability. It is not a useful third Boolean value and not a way for the machine to hesitate thoughtfully. Good timing design reduces the chance that later logic observes such an unresolved physical state. Read the next 3 edge ledger before it runs. Initial Q is 0. D settles at 1 before edge 1, remains 1 through edge 2, then settles at 0 safely before edge 3. The predicted new Q values are 1, 1, 0. Notice that the second edge still performs a capture even though the visible value does not change. State transitions describe the rule applied at each event. A repeated value is not evidence that the clock was ignored. Now place two storage elements side by side. Before an edge, each next state input is calculated from the old outputs. At the shared edge, both capture. Only after their propagation delays do the new outputs become available for the following calculation. This lets us reason as if every participating element reads the same old chapter and then turns the page together. The page turn image maps the separation of state generations. It does not claim perfect physical simultaneity across a real chip. A clock is not universal time for the entire world. It is a physical signal distributed to a chosen timing domain, with finite rise time, delay, and differences in arrival called skew. Designers choose a period long enough for required paths to settle and timing constraints to be met. Some systems use different clocks or asynchronous methods. Our teaching machine uses one declared synchronous model because it makes each committed state change inspectable, not because every computer component in existence changes on one perfect tick. The timeline closes around one precise contract. Data may change and settle between active edges. Setup and hold intervals protect the capture boundary. At the edge, accepted D becomes the next stored value. After propagation delay, Q presents it. The before and after ledger prevents old and new state from being blended into one vague motion. We now have disciplined 1-bit storage. The next step is to repeat it across 8 ordered positions and then feed stored state back through a next state rule. One edge-triggered cell can preserve 1 bit. Our notched carrier contains 8 ordered bits, so place 8 proved cells beneath its 8 positions without changing their order. Every cell receives its own data bit. All 8 share the same active clock edge. Before that edge, the incoming pattern is only a proposed next value. At the edge, the 8 cells capture their corresponding positions. After propagation delay, the stored outputs present the complete pattern together. This aligned group is an 8-bit register. A register is storage with a declared width and shared control used to preserve an ordered pattern as one machine state item. The word register names the container and its capture contract, not the meaning of the bits. The same stored pattern could later be interpreted as a number, character code, instruction field, or raw flags. The notch remains visible because reversing position order would change the pattern even if every cell kept its individual value. Initial register state is all zeros. The incoming carrier settles to 00110011. At the first edge, copy each input position into the matching new state cell. The old state row remains visible until the commit marker crosses it. Then the new row becomes current, no bit slides sideways, and the byte is not poured into a box. 8 local capture events occur under one shared timing contract. Often a register must choose between loading new data and keeping its old state. Put one proved selector before each storage input. Candidate A is the cell's own current output fed back. Candidate B is the corresponding incoming bit. A shared load control selects A for hold or B for load. At the next edge, every cell captures the selected candidate. Hold is therefore not an absence of mechanism. It is an explicit next state choice that sends the old value back into storage. Predict 2 edges. The register currently stores 00110011. A different input pattern waits outside. At edge 1, load is 0, so each selector returns the stored candidate and the register remains unchanged. At edge 2, load becomes 1 after the input has settled, so the new pattern is captured. The incoming wires were active during both edges. The control rule, not mere presence of data, determined which pattern became state. A counter uses the same register and changes only the network that proposes its next input. Feed the stored 8-bit pattern into an incrementer, a combinational module whose contract is to produce the next pattern in a declared counting sequence. A selector chooses either the unchanged state or the incremented proposal. At each enabled edge, the register captures that proposal. The counter is not a special substance that moves by itself. It is a register, feedback, a next state function, and timed capture. An odometer gives the everyday pattern. Its rightmost wheel advances first. When that wheel passes its final digit, it returns to 0 and causes the next wheel to advance. For our counter, each position has only 2 states rather than 10. Starting at the right, trailing ones return to 0 until the first 0 becomes 1. The analogy maps positional carry. It stops at the mechanism. Our stored bits commit under an edge contract, not as visible decimal wheels turning one after another. Begin with all zeros. The first enabled edge captures a pattern ending in 1. At the second, that trailing one returns to 0 and the position left of it becomes 1, giving the ending 1, 0. The third ends 1, 1. The fourth turns both trailing ones to 0 and advances the next position, giving 1, 0, 0. These proposals form between edges and are then captured. Their carry steps never become stored intermediate states. The current low 4 positions are 0, 1, 1, 1. Predict the next enabled state using the rule, change trailing ones to 0, then change the first 0 on their left to 1. The result is 1, 0, 0, 0. If enable is 0 at the edge, the selector returns the old pattern instead, and no count is committed. The incremented proposal may still exist inside the combinational network, but only the selected value crosses the storage boundary. What follows the pattern of 8 ones? Every position is a trailing one, so each becomes 0 and no position remains inside the register to receive the final carry. The next stored pattern is 8 zeros. The counter has wrapped after 256 distinct states. This is not an arithmetic error in an 8-bit contract. It is the consequence of fixed width. Whether a later operation treats the discarded carry as important depends on the exact interpretation and flags we will build. The register contract holds only when every position meets timing. Its incrementer must settle before capture, and outputs must become valid for the following path. Wider storage repeats proved cells, but wider next state logic may need more time. The ledger says what each edge commits. Physical timing analysis decides whether a chosen clock period can realize it reliably. The 8 storage cells now close into a register outline while its selector, feedback route, and incrementer remain available to reopen. We have scaled one remembered bit without introducing a hidden storage principle. We have also produced an ordered cycle of 256 patterns, but we have used words such as next, carry, and count before proving exactly how 8 bits represent whole numbers and what happens when a result does not fit. That fixed width arithmetic is the next promise to earn. The register we built remembers 8 bits at once, but 8 remembered choices are not automatically a number. Their order must matter according to an agreed rule. Keep the register in place while a weight appears beside each bit position. This is the same idea as place value in decimal notation. The digit 2 and 20 means something different from the digit 2 and 200 because its position carries a different weight. The mapping is useful. The limit is that our positions have only 2 possible digits, 0 and 1 rather than 10. Begin at the rightmost position with weight 1. Moving one place left doubles the weight, 2, 4, 8, 16, 32, 64, then 128. A 1 includes its position's weight, a 0 does not. For the pattern 0, 0, 1, 0, 1, 1, 0, 1, the active weights are 32, 8, 4, and 1. Their sum is 45. Nothing inside the pattern announced the word 45. The unsigned interpretation rule supplied that meaning, and the visible weights let us check it rather than trust a conversion. With 8 positions, the smallest unsigned value is all zeros. The largest includes every weight, 1 plus 2 plus 4, continuing through 128, which totals 255. Predict the number of distinct patterns before it appears. Each of 8 positions has 2 choices, so there are 2 to the 8th power, or 256 patterns. They cover 0 through 255 because 0 is one of the values. 8 bits therefore provide a precise range, not an indefinitely expanding number line. Now add 1 to all ones. Every position produces a carry into the next, and the final carry has no 9th position inside this register. The stored 8-bit result becomes all zeros. SE 8 arithmetic wraps, modulo 256. Only the remainder that fits in 8 bits is stored. The extra carry is not silently denied. A separate carry flag records that an unsigned result crossed the available boundary. Predict it. 255 plus 1 stores 0 and sets carry. Fixed width has made the operation exact, including what is lost. The same 256 patterns can support signed numbers if we adopt a second rule called 2's complement. The lower half, from 0 through 127, keeps its unsigned meaning. Patterns with the leftmost bit set represent values from -128 through -1. One dependable calculation is to treat the leftmost weight as -128 while the remaining weights stay positive. Thus, 1, 1, 1, 1, 1, 1, 1, 1 means -1, while 1, 0, 0, 0, 0, 0, 0, 0 means -128. Hold the pattern for positive 127, 0 followed by 7 ones. Add 1, but do not reveal the interpretation yet. The stored result is 1 followed by 7 zeros. Under the unsigned rule, that result is 128. Under the signed 2's complement rule, it is -128. The bit pattern and the addition hardware have not changed. What changed is the question we ask of the result. The signed answer has crossed from the largest positive value to the most negative one, so the overflow flag must report that failure of the signed range. Carry and signed overflow answer different questions. In 255 plus 1, a 9th unsigned bit is needed, so carry is set, interpreted as -1 plus 1. However, the signed result 0 is valid, so signed overflow is clear. In 127 plus 1, no carry leaves the 8th position, so carry is clear, but 2 positive signed inputs have produced a negative signed result, so overflow is set. Neither flag is a general warning light. Each preserves one precisely defined fact about the same fixed width operation. Return the weights to the 8 remembered positions. We can now separate 4 things that often collapse into one word. There is a physical state carrying each bit, there is an ordered 8-bit pattern, there is an interpretation such as unsigned or 2's complement, and there is a calculation whose fixed width may discard information while flags preserve selected facts about it. The register has not learned what a number means. A contract tells the surrounding machine how to use its pattern. That same layered idea will let an 8-bit pattern stand for something that is not a number at all, a piece of encoded text. Keep the 8-bit pattern in the same register and remove the number weights. The pattern has not ceased to exist, only one interpretation has stepped away. To use bytes for text, people agree on a mapping between numbers and elements of writing. The byte does not contain the shape of a letter like a miniature stencil. It carries a number. An encoding rule connects that number to a character identity, and a later font system chooses a visible glyph. Separating those stages will prevent one of the most persistent myths about how text lives in a computer. ASCII is an early, still important agreement using 7 bits to assign numbers to Latin letters, digits, punctuation, and control codes. The digit 3 is assigned hexadecimal 33, which is decimal 51. Notice the distinction on screen. The human number 3, the character called digit 3, and the code value 51 are related but not identical. If a display receives that code under an ASCII-compatible text rule, it may later draw a glyph shaped like 3. The code specifies the character identity, not the artistic outline, size, or typeface. Modern text needs far more than the symbols ASCII can name. Unicode assigns a code point to characters across many writing systems, and UTF-8 encodes those code points as 1 to 4 bytes. UTF-8 deliberately preserves the ASCII range. Values from 0 through 127 use the same single byte. That is why our digit 3 remains 1 byte with value hexadecimal 33. The preservation is a compatibility rule, not evidence that every Unicode character fits in 1 byte. Now follow one non-ASCII example. The character E with an acute accent has code point U plus 00E9. In UTF-8, that code point is represented by 2 bytes, hexadecimal C3 and A9. The 2 bytes are not 2 halves that should each be drawn. Together, under the UTF-8 rule, they decode to 1 code point. A font can then select a glyph. The analogy to a labeled parcel helps only this far. Bytes are the delivered containers, and the encoding is the unpacking rule. Unlike a parcel, the bytes carry no miniature visible object inside them. Even code point and visible character are not always one-to-one. An accented letter can also be represented as a base letter code point followed by a combining accent code point. A reader may perceive 1 grapheme. The data may contain 2 code points. UTF-8 may use several bytes, and the font may compose 1 visible glyph or several position glyphs. These terms describe different layers We need not implement the whole modern text stack in SE8. We do need to know exactly which layer our small machine is handling whenever it stores or changes a byte. Predict the next code before it appears. ASCII places the decimal digits in order. The code for digit 0 is hexadecimal 30, and digit 3 is hexadecimal 33. What code should identify digit 8, counting 5 positions beyond digit 3, gives hexadecimal 38. The visual glyph changes from 3 to 8 only at the rendering layer. In memory, the relevant byte changes from the pattern for hexadecimal 33 to the pattern for hexadecimal 38. This ordered mapping will later let arithmetic cross deliberately between a digit code and the number that digit denotes. Here's the later conversion in slow form. Under the ASCII range preserved by UTF-8, 3 separate key reports produce 3 separate bytes: hexadecimal 33 for digit 3, hexadecimal 2, B for plus, and hexadecimal 35 for digit 5. Subtracting hexadecimal 30 from each digit code produces numeric 3 and numeric 5. Comparing the operator byte with the plus code selects addition. Adding those two entered quantities produces numeric 8. Adding hexadecimal 30 then produces hexadecimal 38, the character digit 8. This works because the 10-digit codes form one consecutive range. It is not a universal recipe for arbitrary text. Return the byte to the register and keep its identity visible. The byte is an ordered group of 8 bits, and encoding maps one or more bytes to code points. A grapheme is a unit a reader may perceive. A glyph is a visible shape chosen by a font and rendering system. 1 byte per character is true only for a limited range under particular encodings. For our final digit, the path is unusually compact because UTF-8 preserves ASCII. We have earned what the pattern can mean. The next problem is physical organization. How can that byte reach different parts of the machine without a separate bundle of wires for every possible journey? Our byte now has a value and an interpretation, but it still sits in one register. If every source had a private 8-wire path to every destination, each new component would multiply the wiring. Keep the learned registers in their fixed positions, while one shared 8-line route grows between them. This route is a data bus. The name describes a shared connection, not a vehicle. A bus does not pick up a byte, remember it, and drive away. Circuitry at the endpoints changes electrical conditions on shared lines, and other circuitry may classify those conditions as an 8-bit value. A building corridor offers one useful relation. Many rooms open onto one shared space, so a person can reach different rooms without a private corridor for every pair. Map rooms to components and the corridor to the shared route, then stop the comparison. There is no tiny courier walking down a wire, and several electrical lines act together rather than one hallway carrying one body. The lesson we keep is controlled access to shared infrastructure. To make that safe, the machine must decide who may place a value on the bus and who may capture it. Watch register R2, which holds hexadecimal 3C. Its output is normally disconnected from the shared lines. When the controller enables R2 as the one driver, each of its 8 stored bits determines the corresponding bus line. After physical settling time, the receiving rule classifies the lines as the same pattern. The highlight marks causal relevance. It is not 8 glowing pellets in flight. In the SE8 trace, a valid bus transfer therefore names one source, one value, and one destination. When no transfer is active, the bus record is invalid rather than an invented 0. The bus is settled to hexadecimal 3C, R1 is selected to receive, and the clock edge has not yet arrived. Predict both states. Before the edge, R1 still holds its old byte. The bus may already display hexadecimal 3C, but a route is not storage. At the edge, R1 captures the 8 classified input bits together. After the edge, R1 holds hexadecimal 3C even when R2 is disconnected and the bus becomes inactive. Source drive, route settlement, and destination capture are 3 distinct events. The before and after ledger keeps them from collapsing into one unexplained motion. Now violate the access rule. R2 tries to drive a 1 on a line, while R3 tries to drive a 0 on that same line. The result is not a useful vote, and it is not automatically either source's value. Real hardware can produce excessive current or an undefined voltage. Our architectural model labels the transfer invalid and forbids the state. This is contention. Incompatible drivers attempt to control the same shared connection. If two sources happen to hold equal patterns, enabling both is still a design error because correctness would depend on an unnecessary and unsafe coincidence. Each bus line has a declared position from bit 0 through bit 7. Bit 0 does not become the most significant bit because its wire happens to be drawn higher or closer to a register. The diagram's geometry helps us follow connections. The wiring contract determines significance. Predict what happens if two lines are accidentally exchanged. The 8 physical conditions may still look valid one by one, yet the destination receives a different ordered pattern. Reliable transport must preserve value and position. It does not preserve a material object, and it does not decide what the byte means. Trace a new transfer without animation. R0 holds hexadecimal A5. R3 holds 0. The controller enables R0 to drive and R3 to capture. During the settle interval, which component has changed its stored state? Neither. At the clock edge, which register changes? Only R3. What does the bus remember afterward? Nothing. R3 retains hexadecimal A5 because its storage cells captured the pattern. If R0 is disabled and no new source is enabled, the trace marks the bus inactive. The answer follows from the roles: driver, shared root, receiver, edge, then stored result, return to the growing machine. Representation is the physical condition used for each bit. Value is the abstract ordered pattern. Location is the state holding component that currently preserves that value. Transport is the controlled causal relation that lets a destination capture it. The bus solves transport by sharing 8 lines under a one-driver rule. It supplies neither memory nor meaning. Our next obstacle is selection on a larger scale. A shared path can reach many places, but the machine needs a precise answer to a different question. Which one of those places is being addressed? Place 8 byte registers beside the shared bus. A data value can now reach the neighborhood, but enabling every register would overwrite all 8 with the same byte. The machine needs a compact way to choose exactly one. An address is a pattern used for that selection. It is not the content stored at the destination. A house number gives a useful everyday relation. It identifies which building a delivery concerns, while the parcel carries what is delivered. The limit is important. Electronic selection is performed by logic, not by a driver reading painted signs and making a conscious turn. One address bit can distinguish two destinations. 0 selects one branch and 1 selects the other. Add a second address bit and each branch divides again, producing 4 unique paths. A third division produces 8. Every added bit doubles the number of distinct patterns, and therefore the number of destinations that can receive a unique address. The tree visible here is explanatory geometry. Actual decoder gates need not be laid out as a literal branching tree. What matters is the exact relation between an input pattern and one selected output. A decoder turns the compact address into a one-hot selection. For every legal address, exactly one output is active. With 3 address bits, pattern 011 activates output 3 and leaves the other 7 inactive. The decoder does not carry the byte stored in register 3. It produces only the permission signal that identifies register 3. Read the promise in both directions. The selected output corresponds to the address, and no second output may be active for that same address. That uniqueness is what protects all unselected storage from an intended single write. Use the doubling rule before the answers appear. How many address bits are needed for 8 locations? 3, because 2 cubed is 8 for 16 locations. 4, because 2 to the 4th power is 16 for 256 locations. 8, because 2 to the 8th power is 256. This works when the full set of bit patterns is assigned. If a system provides fewer destinations than the pattern space allows, some patterns may be unused or reserved. The width alone does not guarantee that every possible address names ordinary memory. SE8 uses 8-bit addresses, so its address space contains 256 byte positions numbered from hexadecimal 00 through hexadecimal FF. Hold address pattern 101-10110. Its active weights are 128, 32, 16, 4, and 2, totaling 182, or hexadecimal B6. Before the decoder reveals its outputs, predict the invariant. Output B6 becomes active and every other output remains inactive. We need not inspect 255 separate failures. The decoder's tested replication rule establishes them together. Keep 2 8-bit carriers visible side by side. The address carrier holds hexadecimal B6. and selects location B6. The data carrier may hold hexadecimal 2D, the byte to be written or the byte returned. Equal width does not make their jobs interchangeable. If hexadecimal 2D appears on the data bus, it does not silently redirect the decoder to location 2D. If hexadecimal B6 appears on the address lines, it does not become the stored content. Names such as address bus and data bus describe contracts at their endpoints, not different species of bit. Compare this decoder with the selector built earlier. A selector chooses one of several data inputs and forwards that chosen value to one output. A decoder takes one compact address and activates one of several permission outputs. With the same number of visible wires, the arrows and promises differ. Predict which module belongs beside a bank of registers during a write. The decoder, because one destination needs an enable. During a read, decoder selection can identify the row, while an output selection network forwards that row's byte. Selection is not one universal box. The direction of the relation matters. The growing machine can now answer which one. Address bits express a compact pattern. A decoder converts that pattern into exactly one active selection. Address wires choose. Data wires carry a byte. Storage cells preserve it. The house number comparison has served its purpose and stops before the mechanism. Decoder logic performs the selection without reading a label. Keep one decoder output connected to one learned register. We will prove that complete path, then replicate it by an explicit rule. That is how a visible bank of a few cells can become addressable memory without asking the viewer to stare at a forest of repeated gates. Memory begins with the storage promise we already proved. A cell can preserve one bit across time and capture a new value only under controlled conditions. Reopen one cell now. Its data input presents a candidate bit, its load permission decides whether capture is allowed, and the clock edge separates before from after. Nothing about scaling may weaken that promise. If the cell is not selected, its next state equals its current state. If it is selected for a write, its next state becomes the input sampled at the edge. Replicate that cell across 8-bit positions. All 8 cells share the row's write permission and edge, while position 0 receives data, bit 0, position 1 receives data, bit 1, and so on. This creates one byte row. The row is not 8 independent mystery boxes. It is 8 instances of one tested rule with a declared position mapping. Predict the result when the input is hexadecimal 5A and the row is selected at the edge. The 8 cells capture 0, 1, 0, 1, 1, 0, 1, 0 in their fixed order, so the row stores hexadecimal 5A. Now place several byte rows under the decoder. Each decoder output connects to the write permission of exactly one row. The global write request alone cannot alter memory. It combines with the selected row signal, so only the addressed row receives an active write permission. Every unselected row sees permission off and preserves its previous byte at the same edge. The visible branch from address to decoder output to row enable is the proof route. Once its endpoints and rule are established, the route can compress, but it must remain recoverable whenever a write is questioned. Test the invariant on 4 rows. Row 1 contains hexadecimal 11. Row 2 contains hexadecimal 22. Row 3 contains hexadecimal 33. And row 4 contains hexadecimal 44. The address selects row 3, the data input presents hexadecimal A0, and write permission is active. Before the edge, all old values remain. After the edge, row 3 contains hexadecimal A0. Rows 1, 2, and 4 retain 1, 1, 2, 2, and 4, 4. The decoder did not move the data into row 3, it granted that row permission to capture the shared input while denying the others. Writing chooses which row may change. Reading chooses which stored row may influence the output. Hold the address on row 2. The output selection path connects row 2's 8 stored bits to the memory data output while every other row remains excluded. No row changes merely because it is read. This is like consulting one numbered drawer only in the limited sense that selection exposes one drawer's contents. The circuit does not open a physical drawer, and the output is a newly established signal representing the stored byte, not the original physical conditions leaving their cells. We can now scale without animating every storage cell one by one. The rule is explicit. There are 8 cells per byte row, with bit position preserved. Each memory row address has one decoder output connected only to that row. A write changes exactly the selected row. A read changes no row and exposes exactly the selected byte. Replicate the proven row and branch as far as the memory map requires. The quiet tiled field is evidence of repeated structure. The active route remains singular and readable. This is SE8 teaching memory, an inspectable model built from the storage, decoding, and selection promises we have earned. SE8 has 256 address selections, but only hexadecimal 00 through EF connect to its 240 ordinary RAM rows. The upper 16 selections are reserved for devices. Nor is this a transistor for transistor portrait of modern dynamic RAM. Real memory technologies differ in cell design, refresh, timing, buffering, and hierarchy. The truthful promise here is narrower. An addressed RAM byte can be read, and an authorized write replaces exactly that addressed byte. Predict a large array case. The address is hexadecimal A6. The decoder must activate output A6 and no other. If write is inactive, every row retains its state regardless of the data input. If read is active, the output selection path represents the byte already stored at A6. If write becomes active and the edge arrives, only row A6 captures the presented data byte. The repeated field need not expand, for the reasoning, address selection, permission, bit position mapping, and edge timing are the complete causal chain. Let the internal rows compress into one stable memory module, but keep its 4 visible obligations at the boundary: an address input, a data output, and declared read or write control. The module earns trust because we can reopen one cell, one row, one decoder branch, and one output path without changing their identities. Capacity tells us how many address bytes exist. It does not tell us what any byte means. The next chapter will drive this module through a real write and a real read, preserving every intermediate register so no instant disappears behind the box. A memory operation is not one glowing arrow, it is a sequence of stable conditions and edge-triggered captures. Keep 4 objects visible: the source register, the memory address register called MAR, the memory data register called MDR, and the selected memory row. The ledger begins before the operation. MAR holds its previous address, MDR holds its previous byte, memory location hexadecimal 80 holds hexadecimal A5, and source register R2 holds hexadecimal 5A. We will write 5A to address 80, then read it back, without allowing any intermediate value to vanish. First, the operand address hexadecimal 80 drives the bus, and MAR is selected to receive. Before the edge, MAR is unchanged while the bus presents the new address. At the edge, MAR captures 80. The decoder now selects location 80, but the stored byte has not changed. An address answers which one. It does not perform the write. If the data source were wrong at this moment, no memory cell should yet be altered. This separate address phase makes the destination stable before any commit is authorized. Second, R2 drives its byte hexadecimal 5A onto the bus, and MDR is selected to receive. Predict the ledger at the next edge. MAR remains 80, R2 remains 5A, MDR becomes 5A. Memory at 80 still remains a 5 because capturing the write data and committing the memory write are distinct controller actions. MDR provides a stable staging place between the shared bus and memory. It is not a second copy with independent meaning. It is the controller visible register currently preserving the byte intended for the transaction. Now the write control is active. MAR still selects address 80, and MDR still presents 5A. Pause before the edge. Which state is allowed to change? Only memory row 80. At the edge, that row captures 5A. Every other row preserves its previous byte. MAR, MDR, and R2 also remain unchanged. The ledger marks memory committed only on this edge. If write control were inactive, even with the same address and data, no row would change. The commit depends on selection, stable data, write permission, and the edge together. Begin a separate read of address 80. If MAR does not already hold the address, the controller captures 80 there first. During the read action, the decoder selects row 80, and the memory output establishes physical conditions representing its stored byte, now 5A. MDR is selected to receive. At the read capture edge, MDR captures 5A. The memory row remains 5A, reading has not consumed or cleared it. The trace marks this memory event committed because the read value has been captured at the module boundary, not because memory content changed. The returned byte is now stable in MDR, but the requesting register has not yet received it. In a final consume action, MDR drives the bus and the destination register captures at an edge. Predict the states immediately before that edge. Memory 80 is 5A, MDR is 5A, and the destination still holds its old byte. Immediately after, the destination is 5A, while memory and MDR remain unchanged. A memory read may therefore involve address, read capture, and consume. Compressing all three into the word load is convenient only after these transfers have been earned. Trace a new case. Address hexadecimal 24 contains hexadecimal C7. R1 holds hexadecimal 09. A write to address 24 is requested with R1 as source, and state the three committed changes in order. MAR captures 24, MDR captures 09. Memory 24 captures 09 on the right edge. Now a read from 24 into R3 begins. MAR selects 24, MDR captures 09 from memory, and R3 later captures 09 from MDR. Address lines never carry 09 merely because it is the content, and data lines never select 24 merely because that is the destination. Close the memory module and leave the transaction ledger beside it. A write is a controlled state mutation. Establish the address, stage the data, then commit exactly one selected byte. A read is an observation followed by transport. Establish the address, capture the selected byte in MDR, then deliver it to a destination. The ledger preserves what existed before and after every edge, so no animated handoff needs faith. We can now store values and recover them. The machine's next need is transformation. Given two stored numbers, how can logic produce their sum and account for every carry? Written decimal addition works one place at a time. We add a column, write the digit that belongs in that place, and carry any excess into the next column. Binary addition keeps that relation but replaces 10 possible digits with 2. The comparison maps place to bit position and carry to a 1 pass toward the next larger weight. It stops there. No person is writing intermediate marks inside the circuit. Proven gates establish output signals according to the same arithmetic relation. We will build one column, test every case, then join 8 copies without hiding the carries between them. Begin with 2 input bits and no incoming carry. 0 plus 0 gives sum 0 and carry 0. 0 plus 1 and 1 plus 0 each give sum 1 and carry 0. 1 plus 1 gives binary 1, 0. Sum 0 in this position and carry 1 to the next. The sum output matches exclusive, or, because it is 1 when the inputs differ, the carry output matches, and because it is 1 only when both inputs are 1. This pair of certified logic relations is a half adder. Its limitation is in the name. It cannot include a carry arriving from a lower position. Every position above the first may receive 3 1-bit quantities: left operand, right operand, and carry in. Their total can be 0, 1, 2, or 3. The sum bit is 1 when that total is odd. Carry out is 1 when the total is at least 2. Check the hardest case. 1 plus 1 plus 1 equals decimal 3. Written binary 1, 1. The local sum is 1 and the carry out is 1. A full adder implements all 8 input combinations. It can be made from 2 half adders and an OR relation, but its promise is the complete 3-input arithmetic table. Place 8 full adder cells in bit order. Position 0 receives carry in 0. Its carry out connects only to carry in 1. That carry out connects to position 2, continuing toward the highest weight. This is an 8-bit ripple carry adder. Ripple describes dependency, not a bead moving through pipes. A later output cannot settle until the relevant earlier carry signal has settled. Every operand bit stays in its position. Only the carry relation crosses from position I to position I plus 1. That repeated mapping is what lets one proven column become a whole word operation. Trace hexadecimal 2D plus hexadecimal 17, which is 45 plus 23. At bit 0, 1 plus 1 produces sum 0 and carry 1. At bit 1, 0 plus 1 plus that carry produces sum 0 and carry 1. At bit 2, 1 plus 1 plus carry produces sum 1 and carry 1. At bit 3, 1 plus 0 plus carry produces sum 0 and carry 1. Keep those 4 carry marks visible. The lower half of the result is 0100 when read from bit 3 down to bit 0, but the operation is not finished because carry still enters bit 4. Continue from the preserved carry. At bit 4, 0 plus 1 plus carry gives sum 0 and carry 1. At bit 5, 1 plus 0 plus carry again gives 0 and carry 1. At bit 6, 0 plus 0 plus carry gives sum 1 and carry 0. At bit 7, 0 plus 0 plus 0 gives some 0 and no final carry. Read the 8 sum bits together. 0, 1, 0, 0, 0, 1, 0, 0, hexadecimal 44, decimal 68. The ledger accounts for every intermediate carry, and 45 plus 23 confirms the result. Try a new pattern before the carry chain responds. Hexadecimal 3F is 0, 0, 1, 1, 1, 1, 1, 1. Add 1. Bit 0 becomes 0 and carries. Each following 1 also becomes 0 and carries through bit 5. Bit 6 receives that carry. While both operand bits there are 0, so it becomes 1 and carry stops. The result is 0, 1, 0, 0, 0, 0, 0, 0, hexadecimal 40. The longest visible change is not evidence that a numerical object traveled. It is the consequence of one local dependency repeated until a position can absorb the carry. If carry leaves bit 7, the 8 sum outputs still contain only the low 8 bits. The 9th fact is available separately as carry out. That is the hardware relation behind the fixed width behavior we interpreted earlier. Signed overflow requires another test, whether the signs of the operands and result are inconsistent for 2's complement addition. The adder produces bit results and carries. Surrounding flag logic preserves the selected summaries. Arithmetic meaning remains a contract over these patterns, not a new physical substance inside the cells. Compress the 8 cells into an adder module only after preserving its inspectable seams. 2 8-bit operands enter. Carry begins at bit 0 and links each position to the next. 8 sum bits and a final carry emerge after settling. The module has no memory of its own. Changing an input can change its outputs until a destination register captures at an edge. We have earned one numerical transformation in full. The machine will also need bitwise logic, shifts, subtraction, and comparison, and control will need compact facts about their results. Those facts are the flags we have already glimpsed. Addition links neighboring positions through carry. Several other useful operations do not. For bitwise and or an exclusive or position I of the result depends only on position I of the 2 operands. Keep the 8-bit carriers aligned while each column applies the gate relation we proved earlier. With hexadecimal A5 and hexadecimal 3C, the shapes of the active bits differ, but the rule never crosses columns. The word bitwise is a scope promise. Repeat one Boolean relation independently at every position. Predict one unseen result. Hexadecimal AA is 10101010. Hexadecimal 0F is 00001111. Exclusive or produces 1 where the aligned bits differ, so the result is 10100101, hexadecimal A5. Because the result is not 0, the 0 flag is clear. Its highest bit is 1, so the negative flag is set under SE8's flag rule. Logical operations clear carry and signed overflow. Those flags do not retain facts from an earlier addition. Not inverts every bit of one operand. In an 8-bit machine, that means exactly 8 inversions. Hexadecimal 0F becomes hexadecimal F0. There is no invisible procession of leading ones beyond the register, because the operation's width is part of its contract. This matters whenever written mathematics suggests an unlimited string of digits. Hardware operates on a declared number of positions. SE8 writes 0, and negative flags from the 8-bit result, and clears carry and overflow for not. A logical left shift moves each retained bit to the next higher position, inserts 0 at bit 0, and discards the old bit 7. A logical right shift moves toward lower positions, inserts 0 at bit 7, and discards the old bit 0. SE8 records the discarded bit in carry. Predict a left shift of hexadecimal 81, pattern 10000001. The stored result is hexadecimal 02. Carry is 1 from the discarded top bit. 0 is clear, negative is clear, overflow is clear by the shift contract. Subtraction can reuse addition circuitry by forming a 2's complement negative of the right operand and adding it. The 8-bit result still wraps modulo 256. SE8 defines carry after subtraction as no borrow. Carry is 1 when the unsigned left operand is at least the unsigned right operand. That convention must be learned rather than guessed from the word carry. 3 minus 5 stores hexadecimal FE, which can be read as unsigned 254 or signed -2. Carry is clear because an unsigned borrow was required. 4 1-bit flags preserve compact facts. 0 is 1 exactly when all 8 result bits are 0. Negative copies result bit 7. It reports the top bit, which indicates a negative value only under the sign 2's complement interpretation. Carry reports carry out for addition, no borrow for subtraction, or the discarded bit for a shift. Overflow reports that a signed addition or subtraction cross the representable range. Flags are like concise margin notes only in the sense that they summarize a larger result. They do not explain it, choose an interpretation, or replace the result byte. Test the distinction again with visible bits. Hexadecimal FF plus 1 stores 0. Carry is set because a 9th unsigned bit was produced. Signed overflow is clear because signed negative 1 plus 1 equals 0. Hexadecimal 7 F plus 1 stores hexadecimal 8 0. Carry is clear because no 9th bit left the adder. Signed overflow is set because positive 127 plus positive 1 cannot be represented. The same adder can therefore set either flag independently. A program must use the flag that matches its chosen interpretation. Comparison in SE8 performs subtraction for its facts but does not write the subtraction result back into the left register. Compare 3 with 5. The internal 8-bit subtraction result is hexadecimal FE, so 0 is clear, negative is set, carry is clear because a borrow is needed, and overflow is clear. R0 remains 3. Compare 5 with 5 and the internal result is 0, so 0 is set and carry is set under the no borrow rule, while the register still remains 5. Comparison prepares control to decide. It does not itself choose what happens next. The machine now has several certified transformations and 4 compact result facts. Bitwise, logic stays within aligned columns. Shifts relocate bits within a fixed width and preserve the discarded bit in carry. Subtraction wraps like addition, with carry defined as no borrow. Comparison updates flags without replacing its source. 0, negative, carry, and overflow retain distinct meanings. Rather than build a separate destination path for every operation, we can place these function lanes behind a selector. Their shared boundary will become the arithmetic and logic unit, or ALU. Keep the 2 operand registers at the entrance and arrange the certified operation lanes without moving their identities. Addition and subtraction, bitwise logic, shifts, not, and comparison. Each lane receives the operand bits appropriate to its rule. A compact operation field controls a selector at the far side. The arithmetic and logic unit is not one mysterious material that changes personality. It is an organized boundary around proven functions and a declared choice. For a given operation code, exactly 1 lane's promised result and flag behavior is allowed to reach the output contract. Operand A comes from the destination register's current value for 2 input SE8 operations. Operand B may come from another register or from the instruction's immediate byte. The operation field names add, subtract, and or exclusive or not shift or compare. These names are readable labels for exact bit relations. The ALU itself is combinational. While operands or selection are changing, its outputs may be unsettled. Controller timing allows them to settle before any architectural register or flag captures the result at an edge. Trace 1 operation, R0 holds 3, the immediate operand is 5. The operation field selects addition. Both operands appear at the adder lane, which produces 8 and the corresponding 0, negative, carry, and overflow facts. The output selector accepts that lane. Before the execute edge, R0 still holds 3. At the edge, R0 captures 8, and the flags capture their new values. All 4 are clear for this operation. The root highlight follows selection and commit. It does not imply that other lane outputs became stored results. Now predict an unfamiliar ALU state. Operand A is hexadecimal AA. Operand B is hexadecimal 0F. The operation field selects exclusive, or the selected result is hexadecimal A5. 0 is clear because the result is not 0. Negative is set because bit 7 is 1. Carry and overflow are cleared by the logical operation contract. If the operation field changed to and with the same operands, the selected result would become hexadecimal 0A with 0 and negative both clear. Operands alone do not determine the result. The declared function selection completes the contract. Comparison uses the subtraction lane but changes the destination promise. The lane computes a fixed width difference so that the flags can be derived, yet the result selector does not authorize a write back to the source register. Hold R1 at 0 and compare it with 0. The 0 flag becomes set, carry becomes set under the no borrow rule, and R1 remains 0. A later branch may inspect 0. This separation shows why an ALU operation is more than a labeled arithmetic symbol. It specifies result formation, flag formation, and whether a register is allowed to capture. The ALU does not remember the selected answer. It continuously relates current inputs and control to current outputs, subject to physical propagation time. The result register and flag register provide the before and after boundary. Before the clock edge, old architectural state remains authoritative while the candidate output settles. At the edge, enabled destinations capture. Afterward, the new register and flag values persist even as the operands or operation field change for another instruction. The clock did not perform the arithmetic. It defined when settled arithmetic became committed state. Let the lanes close into the stable ALU boundary. We may now say the ALU adds or compares, but that sentence is licensed by what can be reopened. Operand selection, one proven function lane, output selection, exact flag rules, and edge-controlled write-back. The box is useful because future traces can remain readable. It is trustworthy because no operation has disappeared from the model. If a surprising flag appears, we can re-enter the relevant lane and reconstruct it from bits rather than inventing a story about the label on the box. The machine can now preserve bytes, select them, transport them, and transform them, but someone still appears to be choosing every control line by hand, which register drives, which operation runs, and which destination captures. To remove that hidden operator, the choices themselves must be represented as stored patterns. A program will place instruction patterns in memory, a program counter will select them in order. The controller will turn their fields into the exact permissions we have used. Control is about to become encoded state rather than an unseen hand outside the frame. Imagine setting every permission before every edge. Choose a source, destination, and ALU function, then advance the clock and begin again. The hardware could calculate, but the sequence would remain in the operator's hands. A recipe offers one useful relation. Written steps preserve choices. The limit is decisive. A processor does not read language or improvise. Its stored steps are byte patterns governed by a precise instruction contract. Place one instruction into the same addressable memory that holds ordinary data. Physically, it is still a byte pattern in a selected location. It becomes an instruction when the processor fetches it under the instruction set rules. Another byte may be treated as a number, text code, or address. The memory cell does not label one pattern program and another data. Meaning comes from the active contract and from how the machine reaches the byte. The program counter, or PC, preserves the address of the next instruction byte. Ordinary progress advances it, jumps and branches may replace it. At reset, SE8 sets PC to the program's origin. The controller copies that address into MAR, memory returns instruction bytes, and PC advances. The visible PC to memory route is a selection promise, not an arrow meaning the program flows as one object. Put 3 instruction pairs at consecutive even addresses. PC selects the first. Its contract changes a register, the next performs arithmetic, the third halts. Change only these memory bytes while keeping processor wiring fixed, and the allowed state sequence changes. That is the stored program gain. Future control actions can be represented, stored, copied, and selected using mechanisms the machine already has. Predict 2 rolls for hexadecimal 05. In an operand position, it may mean immediate 5. At an opcode position, it is decoded through instruction fields and may be illegal. At a data address, a load may copy it without treating it as control. The pattern never announces its role. Controller state, address route, and instruction contract establish whether the byte is fetched as instruction material or accessed as data. Stored program does not require every machine to use one physically uniform array or fetch directly from simple memory on every cycle. It names the principle we are proving. Encoded instructions are held in addressable storage and fetched to direct later state transitions. SE8 uses unified RAM for ordinary code and data. Other machines may add caches, pipelines, separate pathways, and deeper control while preserving an instruction level contract. Suppose PC begins at hexadecimal 20 and every SE8 instruction occupies 2 bytes before a jump which addresses follow, hexadecimal 20, 22, 24, and 26. PC advances through both bytes, so the ordinary next address is the start plus 2. An odd target is illegal because it would begin inside a pair. This 2-byte rule belongs to SE8, not every instruction set. The unseen operator can leave the frame. Memory preserves instruction patterns. PC selects their addresses. The controller fetches and enacts them. But the grammar must be exact, which bits name an operation, choose a register, alter the second byte's role, or make an encoding fault. The next chapter opens one SE8 pair field by field. A stored pattern changes the machine's future because builder and machine obey the same contract. An instruction is not a word that the processor understands as language. It is a bit pattern divided into fields by an instruction set architecture, or ISA. The ISA defines which patterns are legal and what architectural state transition each legal instruction must produce. It is like a form only in the narrow sense that position determines role. A number written in the address box is treated differently from the same number in the quantity box. The limit is that hardware does not read headings. Decoder logic responds to fixed bit positions and values. Every SE8 instruction is exactly 2 bytes. In byte 0, the upper 5 bits form the opcode. The next 2 bits form field A, usually selecting one of registers R0 through R3. The final bit is I, the immediate mode choice for instructions that permit it. Byte 1 is field B, all 8 bits. Opcode decides the operation family. A and I refine that operation. Only then can B be interpreted as an immediate value, a direct address, a branch target, or a register selector. Field boundaries create the grammar. Visual spacing merely reveals them. Decode hexadecimal 11 followed by 03. Byte 0000100001 separates into opcode 00010, A equal to 00, and I equal to 1. Opcode 2 is the load family. A selects R0. I equal to 1 says B is an immediate value rather than a memory address. Byte 1 is hexadecimal 03. The complete instruction is load immediate R003, and its promised transition is R0 receives 3. The flags are preserved. No memory read of address 3 occurs because the immediate field supplies the value directly. Keep byte 1 at hexadecimal 80 and change the first byte. With first byte hexadecimal 14, opcode remains the load family. A selects R2 and I is 0. Now B is a direct memory address. Load memory into R2 from address 80. With an immediate arithmetic opcode, that same B pattern would be the number 128. With a branch opcode, it would be the target address. B has no universal role by itself. Opcode and mode establish the question, then the second byte supplies the answer in the required form. For a register form binary operation, B does not use all 256 values. Its lowest 2 bits select R0 through R3, and its upper 6 bits must be 0. Consider bytes hexadecimal 2, 8, and 02. Opcode 5 selects add, A selects R0, I is 0, and B selects R2. The instruction adds R2 into R0. If B were hexadecimal 82 instead, the low 2 bits would still name R2, but the reserved upper bits would be non-zero. SE8 faults rather than accepting a hidden alias. A strict contract makes malformed programs observable. Decode a new pair before the labels settle. Hexadecimal 29 followed by 05. The upper 5 bits of 29 select opcode 5, add. Field A is 00, selecting R0. I is 1, so B is immediate. Byte 1 supplies 5. The instruction is add immediate to R0, 05, add 5 to the current R0, and write the low 8 bits back to R0, updating all 4 arithmetic flags. If I had been 0, B would need to name a register in its low 2 bits instead. One mode bit changes the operand source, not the addition rule. Try hexadecimal 26 followed by 01. Opcode 4 selects move. Field A is 11, selecting destination R3. I must be 0. B's low 2 bit selects source R1, and its upper bits are all 0. The promised transition is R3 receives the current byte from R1. Flags are preserved. State what would make the encoding illegal. I equal to 1, any non-zero reserved upper bit in B, or an unassigned opcode. A decoder must reject those patterns before execution invents an unofficial meaning. Control flow instructions use the fields more narrowly. Hexadecimal 7-8 followed by 2-0 decodes as branch of 0, target 2-0. Opcode 15 selects branch of 0. A must be 0, I must be 0, and B is the even target address. If the 0 flag is set, execution replaces PC with 20. If 0 is clear, execution preserves the PC that already advanced during fetch. An odd target is illegal because every instruction begins at an even address. The branch byte does not contain a looping action. It specifies one conditional next address choice. The ISA promises architectural results: register values, flags, memory effects, PC behavior, device events, faults, and halting. It need not require every conforming processor to arrange its internal gates exactly like our diagram. The internal organization that fulfills the ISA is the microarchitecture. SE8 freezes one transparent reference sequence so every transfer can be taught and tested. A different implementation could use deeper internal machinery while producing the same declared architectural state for the same program. Contract and mechanism are connected, but they are not the same layer. Use the same decode procedure every time. Split byte 0 into opcode A and I. Let opcode name the instruction family. Check which fields that family permits and whether reserved bits are 0. Interpret B only in the role selected by that family and mode. Then state the exact allowed transition and flag behavior. We can now look at 2 bytes and know what they promise. The remaining question is temporal. How do PC, MAR, MDR, instruction registers, decoder, ALU, and write-back cooperate across clock edges to keep that promise? Show the whole operation before opening it. R0 begins at 3. PC points to hexadecimal 20, where memory holds the 2-byte instruction subtract immediate from R001. 6. Fetch edges collect the 2 bytes. 1 execute edge subtracts 1 and commits 2 to R0. PC finishes at hexadecimal 22, ready for the next instruction. That is the complete promise. Nothing needs to leave the frame while we build it. PC, MAR, MDR, instruction register 0, instruction register 1, controller state R0, flags, memory event, and the 1 active bus transfer keep fixed positions in the ledger. The clock supplies the recurring edge, but it does not decide what each edge means. Controller state supplies that decision. At reset, the next state is fetch 0 address. Its control permissions allow PC to drive the bus and MAR to capture. After that edge, the controller advances to fetch 0 red, whose permissions allow selected memory to provide a byte and MDR to capture. Think of a railway timetable only for the relation between named stages and permitted actions. Stop before intention. The controller is finite state and logic, not a dispatcher thinking about the instruction. Before cycle 0, PC is 20, MAR holds its reset value, the bus is inactive, and no memory event is committed. In fetch 0 address, PC drives 20 onto the bus and MAR is enabled. Predict the post-edge ledger. MAR becomes 20. PC remains 20. Memory has not yet been read. Instruction register 0 and instruction register 1 remain unchanged. The controller records that the address has been latched and moves to the read state. One edge has established which memory location matters. It has not fetched a byte by implication. In fetch 0 read, memory location 20 provides hexadecimal 31, the first instruction byte, and MDR captures it at the edge. Memory content remains 31. In fetch 0 latch, MDR drives 31, instruction register 0 captures it, and PC advances from 20 to 21 at the same edge. Pause and name the states now. MAR still identifies 20 MDR and instruction register 0. Both hold 31, instruction register 1 is unchanged. PC is 21, and R0 is still 3. Fetching an instruction byte has changed controller visible state, not yet the program's arithmetic result. The second byte begins with the same 3-action memory pattern. In fetch 1 address, which value must reach MAR? PC now holds 21, so MAR captures 21. In fetch 1 read, memory at 21 provides hexadecimal 01 and MDR captures it. No arithmetic has occurred. Before the final latch edge, predict PC, instruction register 0, instruction register 1, and R0. PC is 21. Instruction register 0 remains 31. Instruction register 1 still holds its old value. R0 remains 3. Keeping these old values visible makes the upcoming simultaneous changes accountable. At fetch 1 latch decode, instruction register 1 captures hexadecimal 01 from MDR and PC advances from 21 to 22. The 2 instruction registers now preserve 31 and 01 together. Decode byte 0 Opcode 6 is subtraction. A selects R0 and I is 1. Byte 1 is therefore the immediate operand 1. The legal instruction is subtract immediate from R0, 0, 1. The ordinary fall through PC already points 2 bytes beyond the instruction before execution begins. If this instruction were a branch, execution could preserve or replace that ready next address. Controller state becomes execute. R0 supplies operand A, value 3. Instruction register 1 supplies immediate operand B, value 1. The ALU's subtraction lane forms the 8-bit result 2. Its candidate flags are 0 clear, negative clear, carry set because no unsigned borrow was required, and signed overflow clear. Before the execute edge, architectural R0 still reads 3 and the old flags remain committed. The active ALU route is a proposed next state until the controller enables write back and the edge arrives. Predict the final edge. R0 captures 2, 0 remains clear, negative remains clear, carry becomes set, and overflow remains clear. PC remains 2-2 because subtraction does not alter control flow. Memory remains unchanged. The controller marks the instruction complete, increments its instruction index, resets the per instruction microstep index, and returns to fetch 0 address. The next clock edge will use PC2, 2 to begin another instruction. Execute is not a vague phase in which the machine does everything. It is one declared state transition built from an already decoded contract. Use the ledger on a fresh instruction boundary. Controller state is fetch 0 address, PC is 2-2, and the bus is inactive. Name the next 3 committed transfers without seeing them. First, MAR receives PC, so MAR becomes 2-2. Second, MDR receives memory at 2-2. Third, instruction register 0 receives MDR, while PC becomes 2-3. The repeated fetch pattern is now a certified control sequence. We can fade guidance, but not evidence. Controller state, active transfer, and post-edge values remain available for every cycle in the immutable trace. Recompress the 7 edges into fetch, decode, execute, then reopen the state sequence once more. Fetch is 2 address read latch groups because SE8 instructions have 2 bytes. Decode interprets the latched fields and rejects illegal forms. Execute performs the specified transition and write back. PC supplies ordinary sequence, but its value is stored state and can therefore be changed. Flags preserve computed facts that control can inspect. That last connection gives the machine a new power. The next instruction can depend on a result. We can now turn a straight sequence into a loop without relying on an unexplained circular arrow. See the entire countdown before following one path. At hexadecimal 20, subtract 1 from R0. At 22, compare R0 with 0. At 24, branch to address 28 if the 0 flag is set. At 26, jump back to 20. At 28, halt. R0 begins at 3. The program will produce 2, 1, then 0, and halt. The instructions remain in a straight address order. Repetition appears because selected instructions replace PC with an earlier address. The state changes on each visit, so a loop is repeated control flow, not time circling back. The first subtraction has already committed R0 from 3 to 2. The compare instruction at 2 computes 2 minus 0 only for flags. R0 remains 2. The result is non-zero, so 0 is clear, its top bit is clear, no borrows required, and there is no signed overflow. Comparison has not moved PC to either destination. It has created one stored fact the next instruction is allowed to inspect. That temporal separation matters. First compute and capture the flag, then fetch a branch whose contract uses it. A road junction supplies one limited relation. An arriving route can continue normally or take a name turn according to one condition. Map the normal route to the PC already advanced by fetch, the turn to the encoded target, and the condition to a flag, then stop the comparison. There is no vehicle sign reader or moment of deliberation inside the processor. A selector and control logic establish one of 2 next PC values. Branch if 0 chooses the target only when the stored 0 flag equals 1. Fetch the branch at address 24. During its 2-byte fetch, PC advances through 25 and then to 26. Decode reveals branch if 0, target 28. 0 is currently clear. Predict the execute edge. The branch condition is false, so PC preserves the already advanced value 26. It does not add 2 again, and it does not load 28. The trace records branch not taken. The next fetch therefore begins at 26, where the unconditional jump is stored. Not taken means ordinary sequence survives. It is still an explicit branch outcome. And the instruction at 2.6 is jump target 2.0. Its fetch advances PC to 2.8 in the ordinary way. At execute, the jump contract replaces that value with 2.0 regardless of flags. On the next fetch, MAR receives 2.0 and the subtraction instruction returns. No instruction moved backward through memory. PC, a stored address, changed from 2.8 to 2.0. That new state caused the decoder to select an earlier pair of bytes. The loop's backward connection is therefore an exact next address write, not a decorative circular path. Run the second lap with fewer labels. R0 begins the lap at 2. Subtract immediate makes it 1. Compare immediate compares 1 with 0 and leaves R0 at 1, while 0 remains clear. Branch if 0 fetches from 2.4 and preserves fall through PC 2.6 because the condition is false. Jump fetches from 2.6 and replaces PC with 2.0. Predict the state at the new lap boundary. R0 is 1, 0 is clear, PC is 2.0, and the next controller state is fetch 0 address, the structure repeated, the data state advanced. On the third lap, R0 begins at 1. Pause before any result appears. Subtract immediate 1 must store 0. Its arithmetic flags already set 0, but the following compare immediate deliberately compares 0 with 0 and again sets 0 while preserving R0. Fetching branch if 0 advances PC to 2.6 before execute. Now the condition is true, which next address should commit 2.6 or 2.8, the target 2.8. A taken branch replaces the ordinary fall through PC. The jump at 2.6 is skipped because its address is never selected on this path. PC now holds 2.8, so the controller fetches the 2 byte halt instruction there. Halt still performs the full 6 edge fetch. Its execute edge sets the halt latch and enters halted. R0 remains 0. Flags are preserved. No later clock edge performs another instruction. The program did not halt because the loop ran a pre-declared number of times. It halted because changing R0 eventually changed the comparison fact. That fact changed the branch's next PC choice, and the chosen address contained halt. Test the same program from an unseen initial state. R0 begins at 1. Predict the complete control path before it runs. Subtract immediate stores 0. Compare immediate leaves R0, 0, and sets 0. Branch if 0 takes target 2.8. Halt executes. The instruction at 2.6 is never fetched, so there is no backward jump, and only one subtraction occurs. The program bytes are identical to the 3-step countdown. The number of laps changes because architectural state at the comparison changes the branch condition. This is controlled depending on data, with every dependency visible. Recompress the countdown into its causal chain. Subtraction changes R0. Comparison writes a flag without changing R0. Fetch advances PC to the ordinary next address. Conditional branch either preserves that value or replaces it with its target. An unconditional jump can replace PC with an earlier instruction address. Repetition follows because the new PC causes those bytes to be fetched again. Termination follows because repeated arithmetic eventually changes the tested flag. The machine now chooses what happens next using only stored patterns, exact logic, and committed state. We are ready to view the complete processor as one earned system. We have spent a long time opening small things. 1 reliable bit, 1 gate, 1 stored state, 1 register transfer, 1 addition, and 1 instruction cycle. Now the view can widen. Nothing in this complete machine is a decorative box. Every shape returning to the screen is the same shape whose behavior we already tested. The memory stays on the left, the working registers and arithmetic unit stay in the center, and the controller stays above them. We are not beginning a new diagram, we are closing the distances between proven parts. A module earns its place here by making a precise promise at its boundary. A register can hold one 8-bit value and replace it on a declared edge. The arithmetic and logic unit can apply a selected operation to its inputs and expose a result with flags. Memory can return the byte at one selected address, or replace exactly that byte. These promises are smaller than the physical circuitry inside each module, but they are not vague. We can reopen any one of them when a question depends on its interior. The 4 general registers, R0 through R3, are the machine's small working places. They do not decide what their bytes mean. An instruction and the controller determine which register may drive the bus, which destination may capture, and which arithmetic rule is active. The arithmetic unit changes a value. A register preserves the result after that operation is over. That division matters. Without transformation, stored values never develop. Without storage, every result disappears before the next instruction can use it. 3 different kinds of location now meet. The program counter holds the address of the next instruction byte to fetch. The memory address register holds the address currently presented to memory. The 2 instruction registers hold the 2 bytes just fetched. Those jobs must not blur together. The program counter tells the machine where the instruction stream continues. The memory address register selects one location for the current transaction. The instruction registers preserve the selected operation and operand while the controller carries it out. The shared bus is a temporary route, not another storage place. During one transfer, exactly one source is permitted to drive it and exactly one receiver is told to capture. When nothing is transferring, the bus is marked invalid. An idle route does not secretly carry 0. The controller advances through named states that open one route, commit one change, and then close it. Think of railway points only for the idea of selecting one permitted route at a time. No train is hidden in the circuit, and the comparison ends there. The address decoder gives every address exactly one destination. Most addresses select ordinary memory. A reserved upper region selects device registers instead. This is how input and output join the machine without a second kind of instruction. A load from a keyboard register still obeys the load contract. A store to a display register still obeys the store contract. The selected address changes which receiver stands behind that contract, not the meaning of loading and storing inside the processor. Follow one proposed transfer across the whole view. If the program counter contains 16, which module first receives 16? The memory address register. Which structure returns the selected byte? Memory. Which instruction register captures it? The first one, because this is the first byte of the instruction. Only after the edge does the program counter become 17. Every answer comes from a boundary promise already established. The wide view remains readable because we trace one active route while the other routes stay quiet. Name the machine from left to right, memory and device addresses, the address and data registers at the memory boundary, the program counter and instruction registers, the controller, the shared bus, the general registers, the arithmetic unit and flags, then name the contract at each connection. If any connection feels like a leap, that is the place to reopen, not a reason to animate everything at once. The whole SE8 machine is now present. The next test is harder. Can bytes stored in its memory cause a complete result with nobody reaching in to move them by hand? A program begins here as bytes already placed in memory. The first byte of each SE8 instruction identifies an operation and, when needed, a register. The second supplies an immediate value, a direct address, or a branch target. The processor does not read the comments printed beside the program. It receives only these encoded bytes, a reset program counter, the starting register and flag state, and any external inputs scheduled to arrive. From that complete initial state, every later state must follow from the specification. This program waits for 3 separate input bytes produced by 3 separate key presses, 3, then plus, then 5. There is no joint signal carrying the whole expression. The first and third inputs supply the 2 operands. The middle input requests addition. The program converts both digit codes into quantities, verifies the plus code, computes 3 plus 5, converts numeric 8 back into a text code, sends it to the display adapter, and halts. Each input is scheduled only after the processor has entered its corresponding polling loop, so every wait and every arrival remains visible. The first polling loop belongs only to the key press for 3. Before that event arrives, a status load returns 0. Compare sets the 0 flag, and branch returns the program counter to the start of this loop. At cycle 25, the input adapter places hexadecimal 33 in the queue. The repeated status load now returns 1, so the branch falls through. A data load consumes that 1 byte. The later plus and 5 inputs have not happened yet. Neither is part of this signal, this report, or this queue entry. The consumed byte is hexadecimal 33, the text code for the digit character 3. It is not yet the quantity 3. Digit codes are consecutive, so subtracting the 0 code offset, hexadecimal 30 produces hexadecimal 03. R0 now holds numeric 3. The change of meaning did not happen inside the wire or the key. It happened because a specified arithmetic operation transformed one stored pattern into another for a receiver that will use the result as a quantity. The program now enters a second polling loop. This loop waits for the plus key press, not for a combined expression. At cycle 95, a new physical event has produced a new report, and the adapter cues hexadecimal 2b. Status changes independently for this arrival. The repeated polling instructions are the same kind of mechanism as before, but the event is different, its byte is different, and the program has preserved numeric 3 in R0 while it waits. A data load consumes hexadecimal 2b into R2. The controller compares it with the supported plus code, also hexadecimal 2b. Equality sets the 0 flag, and branch on 0 selects the path that waits for the second operand. The plus sign is therefore a genuine input. It chooses the arithmetic operation. It is not a decorative label, and it is not secretly built into the animation. An unsupported operator reaches halt instead of inventing an answer. A third polling loop now waits for the key press 5. At cycle 175, that separate event places hexadecimal 3-5 in the queue. A third data load consumes it into R1. The queue becomes empty again. Only now are all 3 requested inputs present in machine state. Numeric 3 remains in R0, the validated plus code remains in R2, and the text code for 5 is in R1. Subtracting hexadecimal 30 from the byte in R1 produces numeric 5. The addition instruction then names 2 registers. R0 supplies the entered 3, R1 supplies the entered 5. The already validated plus input explains why this addition path was selected. The arithmetic unit computes 3 plus 5, and R0 captures numeric 8. 5 did not appear as an immediate constant, and 3 did not transform into 8 by itself. 2 entered operands met at one selected operation. To display a digit, the program reverses the offset operation. Adding hexadecimal 30 to numeric 8 produces hexadecimal 38, the ASCII subset, and UTF-8 byte for the character 8. A store instruction then places the display data address in the memory address register, copies R0 into the memory data register, and commits that byte to the selected device register. The store does not create pixels by itself. It completes the processor's output transaction and hands the byte to the display side of the contract. The final instruction is halt. The frozen trace contains 246 committed cycles and 32 completed instructions. Its terminal program counter is 42. It records input arrivals at cycles 25, 95, and 175. 3 corresponding data reads, and 1 display byte decimal 56, which is hexadecimal 38. These are simulator records, not values invented by the animation. Rebuilding from the same content address trace must reproduce them. Account for the causal roles before we leave. Which physical event supplied 3, which later event supplied plus, and which comparison let that input select addition, which third event supplied 5, where were the 2 numeric operands stored before the addition. If the 5 key press never occurs, the program must keep waiting. If the operator is not plus, it must halt without a result. Those counterfactuals prove that all 3 inputs matter. Only after 3 plus 5 produces 8 does the program restore the text offset and cross the display boundary. Recognition is not enough. A trace can feel obvious after every answer has been highlighted. So here's a related program the film has not run for you. It begins at address hexadecimal 20 with a value already in R0. It subtracts 1, compares the result with 0, branches to the end if the 0 flag is set, and otherwise jumps back to subtract again. The rules have not changed. Only the starting value and the arrangement of instructions are new. Begin with R0 equal to 3 and the PC at the first subtraction. Before any guidance returns, predict 4 things after that instruction executes. The value in R0, the 0 flag, the negative flag, and the next program counter address. Keep the answers separate. Subtraction changes the register and arithmetic flags. Ordinary fall-through was already prepared during fetch. The instruction does not contain a branch, so it cannot replace that next address. 3 minus 1 is 2, so R0 becomes 2. 2 is neither 0 nor negative in 8-bit 2's complement form. The 0 and negative flags are therefore clear. The program counter points to the compare instruction, 2 bytes after the subtraction began. Notice what made each answer. Arithmetic determined the result determined the flags, and the fixed instruction width determined the fall-through address. One glow on the screen would have hidden those separate causes. Now compare R0 with 0. Predict whether R0 changes. Compare performs a subtraction only to set flags. It does not write the computed result back into the register. R0 therefore remains 2, and the 0 flag remains clear because 2 minus 0 is not 0. When the following branch on 0 reaches execute, will it take its target? No. The condition is false, so the program counter keeps the next address produced by fetch. The next instruction is an unconditional jump to the loop address. It replaces the fall through program counter whether the flags are set or clear. We return to subtraction with R0 equal to 2. Make the next round without help. 2 becomes 1. Compare 1 with 0 clears the 0 flag. The conditional branch is not taken. The jump returns to the loop. At this point, the machine has repeated a route, but it has not repeated a state. R0 is 1 smaller. 1 round remains. Commit to the complete path before it moves. R0 begins at 1. After subtraction, what value and flags are stored? After compare, does the register change? Does the branch keep the fall through address or replace it with the address labeled done? Which instruction executes next? Take the time to answer all 4. The pause is part of the proof. The machine should now be predictable from its rules, not merely familiar from its animation. 1 minus 1 produces 0 in R0 and sets the 0 flag. Compare 0 with 0 leaves R0 unchanged and keeps the 0 flag set. The branch condition is now true, so the target address labeled done replaces the ordinary next address. The jump back to the loop is skipped. The instruction at done is halt. Nothing in the branch recognized that the loop was finished. A stored flag matched a declared condition, and the controller selected the corresponding program counter update. The frozen trace starting from 3 takes 84 cycles and completes 12 instructions before halting. A second frozen trace begins from 1. It reaches the same halt address in 28 cycles after 4 instructions. The shorter trace is not a compressed version drawn for convenience. It follows the same program and the same controller rules from a different initial register state. Compare them at the first subtraction, the compare, and the branch. The exact state difference explains the entire difference in path length. You have now run a machine state the film did not reveal in advance. The transferable method is simple to state and demanding to apply. Identify the current stored state, fetch the exact 2 instruction bytes, apply only that instruction's semantics, record the committed result in flags, then determine the next program counter. Never skip from a mnemonic to a hoped-for outcome. If a new input changed the first value from 3 to 4, how many subtraction rounds would occur and which branch would finally end them? The specification gives enough information to decide. Each key press begins as its own physical event in the keyboard mechanism. In our trace, pressing 3, pressing plus, and pressing 5 happen at different times. Each event produces its own signal change and its own report. The waveform shown for one key press never stands for the other 2 and never carries the complete expression. An input adapter applies the selected layout and interface rules to each report in turn, then offers 3 ordered bytes to SE8. Physical position, key usage, character choice, and encoded text remain different stages. SE8 has 256 possible byte addresses. Ordinary memory occupies hexadecimal 00 through EF. The upper addresses are reserved for devices. Hexadecimal F0 is keyboard status, F1 is keyboard data, F2 is display status, and F3 is display data. The address decoder still activates exactly one destination for every valid address. A device register is therefore reached through the same address selection structure as a memory byte, even though its read or write may cause a device-specific event. Reading keyboard status returns 1 when the input queue contains at least 1 byte and 0 when it is empty. It does not remove the waiting byte. This separation lets a program ask whether a later data read is safe. Writing to the status address is illegal and false. The register is not a little memory cell that happens to sit near a keyboard drawing. It is a defined observation of adapter state with a restricted direction. Reading keyboard data returns and consumes the oldest queued byte. The word consumes is part of the contract. 1 read corresponds to 1 queued input event. In the frozen proof, hexadecimal 33 arrives first and is consumed into R0. Later, hexadecimal 2B is consumed into R2. Later still, hexadecimal 35 is consumed into R1. The queue empties between these scheduled arrivals. No read returns a combined 3 plus 5 payload. and a second read cannot replay the previous event unless another byte was actually queued. The display side has its own direction. In SE8 version 1, reading display status returns 1, meaning the adapter is ready to accept a byte. Writing to display data appends the supplied byte to the device's output sequence. A load cannot accidentally draw, and a store to ordinary RAM cannot accidentally reach the display. Both the operation and the selected address must match the contract. Reserve device addresses fault so that an undefined path cannot be mistaken for a harmless no operation. Watch an input transaction at the processor boundary. A load instruction sends F0 as an address, receives status, and leaves the device queue unchanged. After the program observes ready, another load sends F1, receives the data byte, and changes the queue because the data register contract says read and consume. No special input instruction is hiding in the controller. The same load machinery is reused while the addressed receiver supplies the device behavior. Predict 3 outcomes. First, a load from F0 while 2 bytes are queued. The destination register receives 1, and both bytes remain. Second, a load from F1. The register receives the older byte, and 1 remains. Third, a store to F3. The display output gains the stored byte, and ordinary memory does not change. If those outcomes are clear, memory-mapped input and output no longer require a new data movement idea. They require exact address, direction, and side effect promises. The processor can now touch the world without pretending that a wire carries meaning by itself. A physical event is measured and reported. An adapter applies an interface rule. A device register exposes a byte or accepts one. The address decoder selects that register. An ordinary instruction performs the transfer. At every boundary, ask 2 questions: what physical or stored state exists here, and which rule interprets it. The next boundary begins with hexadecimal 38 in the display register. How can that code select the exact pattern of light we call the Glyph 8? Hexadecimal 38 is a code for the character 8 under the ASCII subset preserved by UTF-8. It is not shaped like an 8. Rotate its bits, enlarge them, or print them directly as a row, and no familiar numeral appears. A code identifies an abstract character within an encoding. A glyph is a particular visible design used to draw that character. The display needs another stored mapping to get from one to the other. Imagine a labeled drawer only for the relation of lookup. The code on the label selects one stored pattern. It does not resemble the contents of the drawer. Our actual mechanism is a small bitmap font store. The incoming code supplies an index, and the selected entry returns several ordered rows of bits. The drawer comparison stops at selection. There are no paper cards inside the display, and the electrical storage method may differ completely from the one in the comparison. Each returned font row is an ordered pixel mask. Position 0 controls one horizontal location, position 1 the next, and so on across the row. A 1 requests the foreground state at that position. A 0 requests the background state. The next stored row controls the next vertical line. Keeping row order and bit order visible is essential. The same count of ones placed in different positions would draw a different shape. Take one row before seeing it light the display. Suppose its 5 visible positions are 0, 1, 1, 1, 0. Which pixel should enter the foreground state? Only the middle 3. The outside 2 remain background. Now swap the first and second positions. The number of ones has not changed, but the lit pattern has. This is the same lesson the Byte taught earlier. Ordered positions, not a bag of identical bits, carry the structure. The adapter presents a row mask and a row address. Selection circuitry opens the corresponding line of the pixel array, and each bit determines the requested state for its column. Repeating that operation for every stored row builds the bitmap from top to bottom. The pixels do not read the character code, and the processor does not draw the curves of the glyph. One mechanism selects glyph data, another maps that data onto physical display elements. A visible pixel is again a physical boundary. In a real display, circuitry controls material that changes emitted or transmitted light. Our monochrome teaching array records only foreground or background at each position. It does not claim to model a particular liquid crystal, organic light emitting, or other display technology. The abstraction is valid for this job because the causal question here is which positions are selected, not the complete physics of producing color and brightness. This direct lookup is deliberately limited to a simple bitmap font and an ASCII subset byte. Modern text may require a Unicode code point, several encoded bytes, combining marks, a grapheme cluster, font selection, and shaping rules that choose or position several glyphs. Those layers are not squeezed into this tiny renderer. The principle we have proved is narrower and exact. For this declared font, one accepted code selects known row mass, and those mass select known pixels. Read the finished image backward. A foreground pixel is active because its row mass contains 1 at that column. That row mass came from the font entry selected for the code hexadecimal 38. The code reached the display register because the processor stored it there. If a single row bit were changed from 1 to 0, which pixel would change? If the code changed to hexadecimal 37, which mechanism would select different row data? Reverse tracing makes every visible mark answerable. Keep the 3 objects distinct. The character is the abstract text element. The glyph is one visible design for it. The pixel states are the physical display pattern produced from that design. Our code selects a font entry. The entry supplies ordered row mass. The adapter applies those mass to the array. That completes one output path. But our input program spent time asking whether data was ready. Must a processor always keep asking, and how can stored information remain available after power is removed? Our SE8 program waits by polling. It loads the keyboard status register, compares the result with 0, and branches back when no byte is ready. Polling is repeated observation by ordinary instructions. It is useful when the program can afford to check often or when the event is expected very soon. Its cost is also visible. Every unsuccessful check consumes fetch and execute cycles that could have been used for other work. Place useful computation on one timeline and status checks on another. If the device becomes ready just after a check, the program notices only when it returns to the status instruction. Checking more often can reduce that delay, but consumes more instruction time. Checking less often preserves more time for other work, but may respond later. Polling is not wrong. It exposes a measurable trade-off between attention spent checking and delay before discovery. An interrupt offers a different control flow contract. When an enabled device signal is accepted at a permitted boundary, the processor preserves enough information to resume the interrupted work and replaces its normal next instruction address with the address of a handler. The handler can inspect or service the device, then perform a defined return that restores the saved continuation. The device does not choose an arbitrary instruction or understand the program. It requests attention through a hardware interface whose effects the processor defines. Predict the necessary state changes. The processor is about to continue at address 40. A device request is accepted. Before the handler begins, what must remain recoverable? At minimum, the interrupted continuation and whatever architectural state the interrupt contract says the handler may disturb. If the return address were not saved, returning would be a guess. If the handler changed registers without saving those required by its calling rule, the interrupted program could resume with corrupted values. Interruption works because preservation and return are specified, not because control magically comes back. Input timing is one problem. Survival after power loss is another. The registers in RAM we have used represent volatile state. Their continued operation depends on supplied power, and the architecture does not promise that their previous contents survive a shutdown. Persistent storage uses physical mechanisms chosen to retain distinguishable states without continuous power. The word persistent describes that boundary promise. It does not mean eternal, immune to wear, or safe without copies and error checks. A magnetic disk can encode states and regions of a rotating surface and move ahead to the requested area. Flash storage can encode states in electronic structures whose measured thresholds persist, while writes and erases obey constraints different from RAM. These are distinct physical implementations. The film keeps their mechanisms separate rather than drawing one universal storage box. Both can nevertheless expose a higher-level interface that reads and writes numbered blocks of bytes. A block interface accepts a fixed-size group of bytes and a block number. It hides many device-specific steps but does not erase them from reality. A disk controller schedules head movement and transfer. A solid-state controller may remap logical blocks, correct errors, spread wear, and erase flash in larger units than a single requested write. Contemporary NVMe devices place commands and completions in memory queues, allowing several operations to be outstanding. That is an interface for organized traffic, not extra intelligence in the stored data. Separate the questions. Polling asks, has the device changed yet? And interrupt says, preserve a continuation and run a declared handler when an accepted request arrives. Persistent storage asks, which physical states and controller rules can preserve addressable blocks without continuous power. None of these mechanisms requires the device to understand the user's goal. Given a sensor that reports once each minute, when might polling be sufficient? Given rare, unpredictable events during heavy computation, what advantage can an interrupt offer? The answer should refer to timing and save control state. Hardware now supplies stored bytes, control transfers, and device interfaces, yet people rarely write a program as a page of hexadecimal pairs. To make programs writable, we build representations above those pairs. The next question is precise. When a person writes a mathematical expression or an assembly mnemonic, which artifact is translated, which program performs the translation, and which bytes actually enter instruction memory? Write a small intention in a human-oriented form. Increase the value called total by 5. That sentence is useful to us, but SE8 has no instruction named total and no rule for English words. A programming language defines a more exact source form. The compiler can translate that source into lower-level operations. An assembler can translate assembly mnemonics into instruction bytes. At every step, one concrete artifact is read and another is produced. Suppose the compiler has assigned the current value of total to R0. The expression total equals total plus 5 can then become the SE8 assembly instruction add immediate R0 5. This is not a universal translation. Another compiler, target machine, optimization choice, or register assignment could produce different instructions with the same intended effect. For this frozen example, the compiler output names one operation, one destination register, and one immediate operand whose meaning is defined by the SE8 instruction set. The assembler applies the frozen encoding. Add immediate uses opcode 5, R0 supplies register field 0, and the immediate mode bit is 1. Together, those fields make the first byte hexadecimal 29. The immediate value 5 becomes a second byte hexadecimal 05, so the assembly line produces exactly 2 bytes 29 and 05. The letters A, D, D I do not enter the processor. They are input to the assembler. Place those bytes in instruction memory and reset the program counter to their first address. The ordinary fetch copies 29 into the first instruction register and 05 into the second. Decode separates opcode, register field, and immediate mode bit. Execute routes R0 and the immediate 5 into the arithmetic unit, then captures the result back into R0. Every layer has now met the same state change, but only the encoded instruction bytes were fetched by the machine. A translator does not preserve the appearance of its input. It preserves specified relationships that matter at the next layer. The source variable may disappear into a register assignment. The assembly mnemonic disappears into opcode bits. A label becomes an address. Comments may produce no machine bytes at all. We can still verify the chain by checking that the generated instruction, when executed from the stated initial state, produces the required result. That behavioral check is stronger than saying the two texts look related. A practical compiler performs more work than this one-line example. It analyzes names and types, checks or assumes language rules, chooses sequences of target instructions, arranges data, and may transform the program to improve a chosen measure while preserving required behavior. Some languages and systems add virtual machines or just-in-time translation. Those are additional specified interpreters and translators. They do not make source words directly executable by the arithmetic circuits we built. Try the reverse direction. The bytes 29 and 05 are stored at the program counter. Using the SE8 field layout, identify the opcode, the selected register, and the operand mode. The result is add immediate to R0 with 5 as the immediate value. Could we recover the original variable name total from those bytes alone? No. That name was not preserved in the machine instruction. A disassembler can reconstruct a valid mnemonic representation, but not every detail of the source artifact that produced it. Keep a ledger of artifacts. The source file contains language constructs. Compiler output contains lower-level instructions or another intermediate representation. Assembly contains mnemonics, operands, and labels. Object or executable data contains encoded bytes plus information needed to place or connect them. The loader eventually places executable bytes and data into memory. The processor fetches those bytes. If someone says the computer runs source code, ask which translation and loading stages are being compressed by that phrase. A language layer is useful because it gives people stronger ways to state structure and intent, while translators produce artifacts accepted by lower layers. The chain remains testable down to exact instruction bytes and machine states, but a useful computer must also begin from reset, share hardware among programs, name stored data, and handle exceptional events. Those jobs belong to another set of enforceable interfaces. We will build them in causal order instead of floating the words firmware, operating system, and file above the machine. A processor cannot begin by asking the system software what to do because no operating system instruction is running yet. It begins from a hardware reset contract. In SE8, reset clears the CPU registers and flags, selects a declared program origin for the program counter, and puts the controller into its first fetch state. Reset does not erase or initialize RAM. A contemporary processor has a different and far more detailed reset contract, but it still requires a defined place and mode from which instruction execution can begin. The first code available after reset is commonly firmware. Software stored in a form the machine can reach at startup. Firmware establishes enough hardware state to continue, may test or configure devices, and applies a platform-defined startup process. The word does not name one universal program. On many contemporary personal computers, UEFI firmware provides standard services and boot choices. Other machines use different firmware and startup arrangements. What matters in the causal chain is that reset reaches executable startup code before an operating system has been loaded. A boot choice identifies where the next loadable software can be found and which agreed format describes it. A boot manager may present or apply that choice. A loader reads executable data from storage, places required sections into memory, prepares initial state, and transfers control to the declared entry point. Each verb is an operation on addresses and bytes. The loader does not awaken a program as an abstract idea. It constructs the memory and register conditions from which that program's first instruction can be fetched. An operating system kernel runs with hardware privileges that ordinary applications do not receive. The processor enforces those privilege distinctions. An application that needs a protected service crosses a declared system call boundary, supplying an operation number and arguments in an agreed form. The kernel validates the request, performs or schedules permitted work, and returns a result or error. This is not a polite convention that any instruction may ignore. Page permissions, execution modes, and controlled entry points make the interface enforceable. To share one processor, the operating system preserves the execution state of one running program and restores another. A process includes an address space view, resources, and at least one thread of execution with a program counter and register state. A scheduler chooses which runnable thread receives processor time according to system policy. Rapid switching can make several programs appear continuous, but at any instant, each core follows its own current instruction stream. The save state ledger explains how work can pause and later continue. A file is a named or otherwise identified sequence of data managed through file system rules. The visible name is not painted onto the storage cells containing the data. Directory records connect names to file metadata. Metadata records such as size, ownership, times, and block mappings help the file system locate and govern the contents. The storage device still transfers numbered blocks. The file system supplies a higher level naming, organization, and consistency contract above those block operations. Trace one file RID, an application supplies a file handle, destination memory area, and requested byte count through an operating system interface. The kernel checks the handle and permissions, asks the file system which logical blocks contain the requested range, and submits storage operations. Device completion eventually makes the bytes available in memory, and the system call reports how much was read or why it could not proceed. The path is longer than a single load instruction, but every stage still changes declared state through a declared interface. Exceptional outcomes need precise names. A hardware fault is a detected condition defined by an architecture or device contract, such as an illegal instruction or forbidden access. An exception is a structured control transfer used to report a synchronous event to software. Some exceptions report faults, while others serve different defined purposes. An error is a broader statement that an operation did not achieve its required result. These words overlap in ordinary speech, but the mechanism shown on screen must identify the exact state and control transfer involved. A bug is a defect in software or its specification, implementation, or interaction that can cause unintended behavior. A vulnerability is a weakness that can be used to violate a security requirement. Malware is software designed to perform harmful or unauthorized actions. One artifact may fall into more than one discussion, but the terms are not synonyms. A crash does not by itself prove malware, and a programming bug is not automatically exploitable. The film uses the smallest accurate term supported by the observed mechanism. Put the startup chain in causal order. Hardware reset establishes the first processor state. Firmware executes from a reset reachable location. A boot choice locates the next software. A loader places executable material into memory and transfers control. The operating system kernel establishes protected services and resource management. A later loader can construct an application process. If the application opens a file system and storage interfaces translate that request into block transfers. Reverse any adjacent pair and ask whether the later stage would yet exist to perform its job. Software layers do not float above hardware. They are programs and data structures whose interfaces are enforced by processor state, memory protection, control transfers, storage formats, and device operations. Each layer lets the next user work with a stronger promise. A process instead of raw registers, a file instead of loose blocks, a system call instead of unrestricted device access. Yet every digital layer eventually meets physical measurements again. What happens when the input is not already a clean 0 or 1, but a changing sound, temperature, or voltage? A microphone voltage can vary through a continuous range as sound changes. To represent that signal with numbers, a system must answer two separate questions. At which moments will it measure, and which numeric level will stand for each measured amplitude? Keep time on the horizontal axis and amplitude on the vertical axis. Without both axes, sampling and quantization are too easily mistaken for the same operation. Sampling selects moments in time. At each marked instant, the sampler observes the input condition. Values between those instants are not separately recorded by this sample sequence. Taking samples more frequently supplies more time positions, taking them less frequently supplies fewer. The sample rate therefore concerns spacing along the time axis. It does not determine how many amplitude values each sample can represent. Quantization selects among representable amplitude levels. A measured value between two available levels must be assigned according to a declared rule, often to the nearest level within range. The difference between the measured value and the chosen level is quantization error. Adding more representable levels can reduce that difference, but it does not add missing sample times. Quantization concerns the vertical axis. An analog-to-digital converter combines a physical measurement path with sampling, quantization, and an encoding of the chosen level as bits. Its result is limited by input range, reference accuracy, noise, timing, and the number of output codes. The code is not the original physical signal stored whole. It is a discrete statement about one measurement under the converter's declared conditions. Here are two different changing signals and a sparse set of sample times. At every marked instant, both signals cross the same value. What sample sequence will the converter produce? The same one. From those samples alone, the receiver cannot know which of the two unsampled paths occurred. This ambiguity is aliasing. A suitable input filter and a sample rate chosen for the signal bandwidth are part of the measurement contract, not optional decoration added after conversion. The outward path uses a digital to analog converter to map codes to physical output levels over time. A simple converter may hold each requested level until the next sample, producing a stepped waveform. A reconstruction filter can smooth the high-frequency components introduced by those steps and recover an intended band-limited signal within stated limits. The output is a new physical signal constrained by the codes, timing, converter, and filter. It is not the original input emerging unchanged. Identify the possible losses. Sampling can fail to distinguish changes that occur between chosen times. Quantization replaces a measured amplitude with one available code. Values outside the converter's input range may be clipped. Noise and component limits can disturb the measurement. Later, compression or processing may discard further detail by design. Naming these boundaries does not make digital representation unreliable. It states exactly what the representation can and cannot preserve. Given a new graph, point first to the sample times, then to the available amplitude levels. Ask which changes could occur unseen between samples, which measured values share one quantized code, and which physical limits define the valid input range. On the output side, identify the converter levels and the reconstruction filter. The digital machine now has an honest boundary with an analog world. We can finally compare our clear teaching machine with modern systems, provided every new mechanism states which old contract it preserves. SE8 makes one instruction's path deliberately visible. A modern processor may contain many overlapping operations and layers that are hidden from an ordinary program. The comparison must therefore begin with a contract, not a picture of complexity. A program sees an instruction set architecture, defined instructions, registers, memory effects, exceptions, and other observable state. Implementation is allowed to become deeper only while producing outcomes permitted by that architectural interface. Begin with a load from an address. In SE8, the visible memory path reaches the one unified store. A modern system may first search one or more caches containing copies of recently or predictably useful blocks. If the required block is present and valid, the cache can satisfy the load without waiting for main memory. If it is absent, lower levels are consulted and a block may be brought closer. What is preserved for the program is the load's required value and memory ordering behavior. What is hidden is where the implementation found the data and how long it took. SE8 completes fetch, decode, and execute steps in an easy-to-follow sequence. A pipeline overlaps stages belonging to different instructions. While one instruction executes, a later one may decode and another may be fetched. This is like an assembly line only in the limited sense that different stages work on different items at the same time. Instructions are not identical products, and dependencies can force the pipeline to wait, redirect, or supply a result from a later stage to an earlier consumer. Place add R0, R1 immediately before store R0. The store needs the new value, but that value may not yet have reached the ordinary register write stage when the store begins. The implementation must preserve the dependency. It may delay the store, forward the new result through an internal path, or use another correct mechanism. Allowing the store to use the old R0 would violate the architectural program. Overlap changes timing inside the processor. It does not cancel data dependence. A wider processor may inspect several waiting instructions and execute a later independent operation while an earlier one waits for data. This is out-of-order execution. The phrase describes internal scheduling, not permission for later instructions to rewrite the program's meaning. The processor tracks operands, dependencies, destinations, and possible exceptions. Work may finish internally in a different order, yet architectural results must become visible according to the machine's retirement and memory ordering rules. Ordered retirement is the boundary where completed internal work becomes committed architectural state in program order. Suppose an early load will fault, while a later independent addition has already produced a result internally. The machine must not present a state in which the later instruction appears committed past an earlier exception when its architecture forbids that outcome. Tracking and retiring instructions in order lets aggressive internal work preserve a precise external history. The before and after ledger survives even when the path between is crowded. Add a second core and one fact changes immediately. There is no longer one program counter and one register state for the whole processor. Each core has its own current instruction stream and architectural state. They may access shared memory, which creates obligations absent from the single core SE8 view. If one core writes a location while another reads it, cache coherence mechanisms help their caches maintain the system's declared view of each memory location. Coherence does not decide when the program intended communication to occur. Programs need synchronization operations and memory ordering rules to coordinate shared state. Imagine two cores both reading a counter, adding one, and writing it back. If both read the same old value before either write becomes visible, one increment can be lost. The arithmetic on each core is correct. The combined update is not atomic. Locks, atomic read, modify, write operations, and other synchronization tools create stronger contracts for selected shared transitions. Parallel execution therefore adds coordination problems, not just more speed. In SE8, an 8-bit address directly selects one architectural location. Contemporary processes usually issue virtual addresses. Translation structures map virtual pages to physical memory frames and attach permissions such as readable, writable, or executable. A translation look-aside buffer may cache recent mappings. A missing mapping or forbidden access can raise an exception so software can respond. What is preserved is the process's address space contract. What is translated is the address used to reach physical memory. A scalar SE8 arithmetic instruction changes one 8-bit destination. A vector instruction can apply related operations across several packed elements under one instruction. If 8 pairs of image values need the same addition, several lanes can work in parallel. Element width, lane count, masking, overflow behavior, and memory layout are part of the vector contract. The advantage comes from regularity across many related items. A branch-heavy sequence in which every item needs different control may use those lanes poorly. A graphics processing unit provides many execution resources designed for high throughput across large groups of related work. A program launches organized groups of operations and supplies data through explicit memory spaces and synchronization rules. The GPU does not make every problem fast. Work with abundant parallelism and regular data access can occupy its resources well. Serial dependencies and divergent control can limit that use. The preserved promise is again an execution and memory interface, not a claim that the internal machine resembles one enlarged SE8 core. A modern solid-state drive also preserves a simpler outer contract while changing its interior. The host submits reads and writes for logical blocks. Inside, a controller maps those blocks onto flash locations, corrects some errors, moves data as cells where, collects still valid data before erasing larger blocks, and may keep several commands in flight. A logical block number is not a permanent physical cell address. The controller maintains the mapping that lets the outer storage interface remain stable while the physical placement changes. Classify each addition to the modern view. A cache hides some access distance while preserving load and store results. A pipeline overlaps stages. Out of order, scheduling reorders internal work, while retirement controls architectural commitment. A second core replicates execution state and adds coordination obligations. Virtual memory translates addresses and enforces permissions. Vectors and GPUs multiply related operations. A storage controller hides physical placement behind logical blocks. If a mechanism cannot be described by what it preserves, overlaps, replicates, translates, or hides, the comparison is not yet clear enough. Modern machines are not SE8 with more boxes, and SE8 is not a miniature laptop. The teaching machine gave us clean contracts: stored instruction, architectural state, address, operation, committed result, and device boundary. Those same questions remain useful when implementations become concurrent and layered. We are ready to return to the opening key press. This time there will be no unexplained gap. At each transition we will name the state that exists, the mechanism that receives it, and the rule that determines what happens next. The opening composition returns, the 3 keys we press, the machine, and the empty display. The inputs are 3, plus, and 5 in that order. We begin with this whole root, then build its explanation without losing the whole. Every carrier will remain visible only when a receiving mechanism gives it a role. Physical event, report, text byte, status, instruction, register value, output code, font row, or pixel. Most importantly, the 3 key presses remain 3 events. No single waveform or report stands for the complete expression. Pressing 3 moves one key mechanism through a physical transition. Its sensing circuit records that key position in one report. Later, pressing plus creates a second transition and a second report. Later still, pressing 5 creates a third. The signal we inspect for the first key press belongs to that first event alone. It is not a joint signal for 3, plus, and 5. These reports preserve order, but none yet asserts a text character until the layout and modifier rules are applied. The input adapter applies those rules separately to the 3 reports. In this setup, it produces 3 ordered text bytes: hexadecimal 3-3 for the character 3, hexadecimal 2, B for plus, and hexadecimal 35 for 5. Each byte reaches the queue at its own scheduled time. They are not packed into one magic expression byte. The order is preserved because the program consumes the oldest available byte before waiting for the next one. Meanwhile, SE8 executes 3 polling stages. Before each expected byte, status is 0, compare sets the 0 flag, and branch returns to that stage's wait address. The 3 bytes arrive at cycles 25, 95, and 175. Each arrival changes status for its own queue entry. The next status load sees 1, the branch falls through, and 1 data load consumes exactly 1 byte. The processor never detects a key shape or a complete equation. It observes ordered device state through addresses F0 and F1. Open 1 instruction fetch all the way. The program counter drives the bus, the memory address register captures it, and the decoder selects exactly 1 byte. Memory drives that byte into the memory data register. The first instruction register captures it as the program counter increments. The sequence repeats for the second byte, then Decode selects the operation and its operand. This same proven mechanism fetches each polling, conversion, comparison, branch, addition, and store instruction. Close the inset. The architectural transfer remains the same while the program advances. The first data load sends address F1 through the ordinary memory path. The keyboard data register returns and consumes hexadecimal 33. R0 captures the same ordered 8-bit pattern. Subtracting hexadecimal 30 produces numeric 3, which R0 preserves while the program waits for the other inputs. Nothing about this operation anticipates 5. It establishes only the first operand from the first key press. The second data load consumes hexadecimal 2b into R2. A compare instruction checks it against the program's supported plus code. Equality sets the 0 flag, so the following conditional branch selects the addition path. This is where the operator input has causal force. The controller does not add because the diagram displays a plus sign. It adds because the entered operator byte matched the declared code and the branch followed the corresponding stored instruction route. The third data load consumes hexadecimal 35 into R1. Subtracting the digit offset produces numeric 5. Now the addition instruction routes R0 and R1 to the arithmetic unit. The first entered digit supplies 3, the second entered digit supplies 5. The validated operator has selected addition. The carry-linked adder therefore computes 3 plus 5, and R0 captures numeric 8. The result has 2 operands and 1 operator. No input has been omitted or replaced by a hidden constant. A second addition restores the digit code offset. Numeric 8 plus hexadecimal 30 produces hexadecimal 38. The ordered bits in R0 now match the declared text encoding for the character 8. The physical register cells are still the same register cells. What changed was their stored pattern. The role is justified by the operation and by the display interface that will receive the result. Keeping that receiver visible prevents the pattern from appearing to announce its own meaning. The store instruction places address F3 in the memory address register and hexadecimal 38 in the memory data register. On the right edge, the decoder activates the display data register, not RAM, and the adapter accepts the byte. The simulator records 1 output event with decimal value 56. The processor's job in this transaction ends at that committed interface. It has supplied a code, it has not drawn a line, chosen a typeface, or illuminated a pixel. The display adapter uses hexadecimal 38 to select the font entry for 8. Ordered row masks emerge from the font store. For each row, 1s select foreground pixels and 0s select background pixels at matching columns. Row after row commits until the complete bitmap is present. The visible 8 is therefore supported by a chain of selections. Output address selected the adapter, text code selected the glyph entry, row address selected the display line, and each row bit selected a pixel state. Now explain the route without following the highlight. Which physical event produced each of the 3 reports? Which adapter created hexadecimal 33, 2b, and 35? Why did the program wait separately for them? Which operation converted each digit code? Which comparison gave plus its selecting role? Which 2 registers supplied the operands to addition? Why was hexadecimal 30 restored? And which address handed hexadecimal 38 to the display? The frozen trace contains 246 cycles and 32 instructions. Every link has a named state and receiving rule. The labels can now begin to leave, but the causal structure remains. 3 key mechanisms change physical state at 3 different times. The keyboard interface creates 3 reports. The input adapter applies layout and text encoding rules separately, producing ordered bytes for 3, plus, and 5. The device queue exposes each arrival to a polling program. 1 event, 1 signal change, 1 report, and 1 consumed byte remain linked. No signal is allowed to stand for all 3 inputs. Inside the processor, the program counter supplies instruction addresses and memory returns encoded instruction bytes. The controller decodes them into permitted routes. R0 preserves numeric 3. R2 preserves the plus code long enough for comparison to select the supported addition path. R1 preserves numeric 5. Only then does the arithmetic unit add the 2 register operands and produce 8. A later addition restores the text offset. No single module and no single input performs the whole result. Their boundary promises compose it. At the output boundary, an ordinary store selects the display register. The receiving adapter treats hexadecimal 38 as a text code and selects the font entry for 8. Ordered row masks select pixel states, and light reaches the viewer as the glyph 8. The final mark was not hidden inside the key for 3, the key for plus, or the key for 5. It is the last state in a sequence whose 3 distinct inputs have now been combined by 1 verified arithmetic operation. An 8-position carrier has appeared in many roles: keyboard report field, digit code, operator code, numeric operand, instruction byte, address, font row, and pixel mask. Its geometry did not explain those roles. The receiving mechanism did. A register holding 0011100 stores an ordered pattern. The display adapter may interpret it as code 38. A numeric instruction may interpret the same bits as 56. A font row receiver may treat another octet as 8 on or off pixel choices. The entered 5 is an input operand, not an immediate value concealed in the program. The machine does not need a hidden observer to recognize the purpose of each byte. Physical structures enforce valid signal ranges, logic implements Boolean relations, feedback and clocked storage preserve state, decoders select destinations, instruction encoding select operations, software arranges those operations into longer procedures, device interfaces translate between stored values and external events. The result follows because each receiving mechanism responds to its present inputs and state according to its construction and specification. Begin at the remaining 8 and travel backward once. Which pixels are active, which font rows selected them, and which output code selected that font entry, which store committed the code, which register held numeric 8, which addition used R0 and R1, which 2 conversions produced numeric 3 and numeric 5, which comparison validated the operator in R2, which 3 data loads consumed the ordered bytes, which 3 reports and physical key events produced them. If every answer names both a state and a receiver, the chain is complete in either direction. This completed path does not claim that every computer uses SE8, one internal bus, this font, this keyboard interface, or this display technology. It demonstrates a method that survives those changes: state, the physical encoding, the boundary contract, the stored state, the operation, and the observable result. Modern systems add depth, concurrency, and translation, but they remain answerable at their interfaces. Where a detail has been abstracted, the abstraction names what it promises and can be reopened when the question requires it. The labels are gone. The 8 remains. Behind it is no unexplained leap, 3 physical key events, 3 reports, 3 encoded symbols, 3 waits and data reads, 2 digit conversions, 1 operator validation, 1 register-to-register addition, an output code conversion, an address store, a selected glyph, and committed pixels. The signal shown for any one input belonged only to that event. The machine produced the visible result through finite, testable changes of physical and stored state, and every part supporting the whole has been earned.